Good morning, everybody. I hope you can hear me and see my screen. Today, we will start by error correction, and error correction is actually one of the cornerstones that is making quantum computing working. Because if you want to execute millions of gates, then this means you need to have very low error rates. We start very easily with classical codes. This is to make all the necessary background much easier to understand. We talk about why we need quantum error correction, what are the differences to classical noise sources in the quantum world. Then we talk about the first quantum code, the very easy repetition code is very similar to some of the classical codes. Talk about the stabilizer formalism, which makes this more general, and what is fault-tolerant quantum computation. We introduced the surface code, which is one of the standard tools that most people should know about if they talk about quantum error correction, and a bit about decoding and how you would realize quantum memory. So we start with the classical codes. So this is very easy. The setting is the following. Imagine that you want to send a k-bit message. That means a message that consists of k zeros and ones across a noisy channel. And this kind of channel is such that it flips the bits independently with very low probability. So if you send a zero, then with very high probability, you will get back a zero. And if you, with slight probability, very small, let's say 0.1%, it will be flipped from 0 to 1 or from 1 to 0. And then the question is, how would you protect from this kind of a noise? A very easy way to do this, it would be to just be redundant, repeat the information. So instead of sending a 0 once, you send it, let's say, 3 times. You send it through the channel, and if the probability is identical, but independently distributed with very high probability, if p is small, you will get back your zero string, 0, 0, 0. With a very small probability, one of the bits will be flipped. With a much smaller probability, again, 2 bits will be flipped, and almost negligibly with smaller probability, you will get 3 bits flipped. So let's say we receive 0 and 0, and then assuming this kind of noise model, it's very natural to assume that we just take a majority vote. What do we have the most? It's 2 times 0 and only 1 times 1. So we will decode it to be, okay, the sender wanted to send us a 0. This is the very easy setting. So a bit more formalizing this, in general, you have a k-bit message X that you want to encode into n bits. And this encoding typically has this calligraphic E, so that is the encoding step, E of X. Then you send your encoded message through a noisy channel, and then you will have to have a decoder that wants to get back the X tilde that should be close or identical to your X that you sent in. Another thing that is common to use is the word code word. This is just an element of the image of the encoder E. And the set of all code words C is then the image of E. As an example, the 3 repetition code, you have k equals 1. That means you want to encode a 1-bit message into n equals 3 bits. So then your code words are simply 0, 0, 0 and 1, 1, 1. This is not very surprising, but in general, this can be quite different. So if 1 or 2 bits are flipped, then the error can be detected. If 3 bits are flipped, then you cannot distinguish 0 and 1. And this is what we typically call an undetectable error, or typically it's called a logical error, because it makes the logical 0 into a logical 1 and vice versa. And this can neither be detected nor corrected, of course. So let's move on a bit further. A simple parity check code is when you want to send a 3-bit message and you just append a 4th bit, which encodes the parity of the first 4. the first three. So the fourth bit set that you send in addition to your message will just be A plus B plus C modulo 2 because we live in the world of bits. The properties of this is that the set indicates, of course, the sum. So if it's even or odd, if A, B, and C is even or odd. And any single bit error can be detected by this. So if A, B, or C is flipped, then it will not coincide with the modularity that is encoded in set. And vice versa, if set is flipped, then, because that can also happen, of course, then it no longer corresponds to the parity of A plus B plus C. The limitation of this is that we can detect this one bit flip, but we cannot correct it. We have no way of knowing where this happened. So Hemming introduced a method that could also correct errors using what is called parity check bits. So the idea is that, for instance, as an example, you would want to have a 4-bit message, A, B, C, D, and you append 3 parity checks. So you have set 1 that is A plus B plus D, set 2 is A plus C plus D, set 3 is B plus C plus D. So this is it should be a calligraphic E. Calligraphic E of your message, you also append these parities. This is easier to view visually. So imagine that set 1 is checks the parity of A, D, and B. Set 3 checks the parity of C, D, and B, and set 2 of A, D, and C. So this is much easier to view typically. So if a single bit is flipped, a certain parity checks will fail here. So let's assume A is flipped, then set 1 will not correspond to the parity again, and set 2, so set 1 and set 2 will light up as this, there's something wrong, but set 3 will remain intact. And this leaves the only possibility that A has been flipped. And you can play the game for any combination. So this pattern of where your parity checks fail will give the indication of where the position of the error is. So we can move on from this to generalize this a bit into linear codes. They generalize this transmitting a message of parity check bits. And we formalize this, that a linear code is given by a matrix G, which typically is called a generator message, which encodes the message by this y equals G times X. So this is just matrix multiplication. And of course, this is a linear code because this is a linear equation. The message X has typically length K and is supplemented with M parity check bits, such that the encoded message Y has length N equals K plus M. So typically the generator G has this form where you have the identity matrix on top, and then you have your encoding A here. And this A defines the parity check operation. So one of the standard examples to give here is the 7-4 Hemming code. You can see on top you have the identity matrix, which corresponds, if I go back slightly here, this corresponds to, no, I don't find it. Maybe you shouldn't have gone back. This just corresponds to repeating your message. But then here, this next the last 3 rows, they encode this parity checks. So A plus B plus D, just as we had before. So yeah, so if you multiply your message X, then it's exactly what we just had before. It's just formalized with this matrix G. It's just nice to have this way because then you know certain properties by looking at the matrix. The code words are all a set of all linear combination of the columns of G. So to find all code words, you just they are all of the form where you have A1 to AK, 0 and 1, and you have all possible combinations of the columns. You also see that elementary row and column operation of G do not change the code because the code is given by the image of G, and elementary row and column operations don't change. You can get this all same combinations. So typically, by whatever form it has, by Gaussian elimination, you can always transfer G into the standard form, where you have the identity on top and your parity check matrix A and the bottom. There's an equivalent representation of a linear code, which is given by the parity check matrix H. So then it's defined by the equation HY equals 0. So H is an m by n matrix, and Y is a code word if and only if it is in the kernel of H, which means that H of Y equals 0. So the set of all code words is just the kernel of H, as I just said. And for the 7.4 Hamming code, it looks like this. You already see probably how you can get to this, and we will see this in the next slide. So if I receive a word Y tilde, which has been encoded, sent through the channel, then it can be checked for errors by just evaluating H times Y tilde. And errors can often be located and corrected using this method. In general, if you have the generator matrix form G with the identity on top and A here, then the corresponding parity check matrix is just given by this. So that's what we also saw for the 7.4 code. So why would you use the parity check matrix in general? Why would we prefer it? So a received vector, so Y is our original code word, and then we add what is called an error vector, E. So E is the bits that are flipped, but we receive the combination of this. So if you apply the parity check matrix H, then you can see that, of course, Y is a code word, so H of Y, H times Y is 0. So you're left back, the only thing that you observe is H times E. And this is typically called the syndrome, S, which is H of E. The code word doesn't matter in this. It's 0. The syndrome identifies errors by revealing violated parity checks. So each of these entries of this vector S indicates a violation if it's equal to 1. If it's 0, then it's not. This parity check is not violated. And then the decoding finds the most probable error that explains the syndrome S. There's again some noise from someone. A violated parity check equation points to a specific bit which is involved in the error. So let's see this again for the 7.4 code. So you have 8 possible syndromes, 2 to the power of 3, because you have 3 syndromes or parts of the syndrome. So if it's all 0, you don't need to do any correction. If it's 1, 0, 0, that means set 1 lights up. Then you need, I think I messed this slide slightly up. I need to think now. So if set 1, if 1, 0, 0 is light up, that would mean that D would need to be corrected. Yeah, I need to correct this before we upload it. But you can play the game for any combination. So if set 1, set 2, set 3 light up, so it's 1, 1, 1, this is correct again, then D should be corrected. So you can make this table for any code. But as you already saw, that it quickly gets quite large. So in general, there are 2 to the power of n possible syndromes. And we want to define an efficient decoder as an algorithm that accomplishes this task in polynomial time in n. So if you just go through all possible combinations, it will be exponential, which we want to avoid. So an efficient decoder should do this in polynomial time in n. So the parity check matrix H, let's assume that we have a certain distribution of the errors, or a certain probability that the errors happen. So given a syndrome S, we want to find the most likely error E. And the goal of an ideal decoder is to find the vector E that maximizes the probability given a syndrome that the error has occurred. So if you look again at this probability that we want to maximize, PE given S, we can apply, of course, Bayes' rule. which is just the rule, you can immediately observe that P of S does not explicitly depend on E, so it can be ignored for solving the maximization problem over E. Another observation is that P given E, P of S given E, it's either 1 or 0. And this is because an error must satisfy that it actually gives the syndrome. So either gives the syndrome, and then the probability of observing S given E is 1, otherwise it's 0. So our optimization problem can be recast that you want to maximize the error E, the probability of E, given that it actually gives you the syndrome. So only of the ones that give the syndrome, you want to maximize that this error has occurred. So a special case is that you have IID noise, where it's just given by the product. So the probability that it flips is P, and that it remains the same as 1 minus P. Then you can simply write it down by this formula. P of E is the probability of all the flips, 1 minus P of the probability of nothing has flipped. And E, of course, is the Hamming weight of E. And this means that if P is smaller than a half, the probability of PE increases when the weight of E decreases. This can be immediately seen from this formula. And therefore, in this case, our optimization problem reduces to finding the error of minimum weight, minimum Hamming weight, that satisfies that it gives us the syndrome. So we want to minimize the Hamming weight of E such that H of E equals S. And if there is actually for this, we have a Jupyter notebook, but I think we will provide it, but we'll not go through it because we have quite a lot to cover. Any decoder that explicitly solves this kind of posterior maximization is called a maximum a priori decoder and is considered an ideal decoder. The challenges with this is that, as I mentioned already, a naive approach requires searching all 2 to the power of n possible error vectors, and this is exponential, so it's not an efficient decoder. So, and in general, this map decoding problem is NP complete. That means unless P equals NP, there's no polynomial time algorithm, and this no one assumes that P equals NP. We want to have an efficient decoding, and this for special codes, for instance, Hamming codes or repetition codes, they allow for polynomial time decoding, but in general, we have to do with heuristics. So a heuristic is an approximate solution for this map decoding that is efficient and performs well in practice. So you don't have guarantees in general, but it's a reasonably well-functioning code that actually works in practice most of the time. And typically, or one of the things that you can look into are these belief propagation algorithms. They are iterative linear time algorithms. They exploit this factorization over a graph, which is called a tanograph. This is basically just a teaser if you want to go deeper into decoding. I'm not going to explain this in more detail. And this is widely used both in classical error correction and also in quantum error correction. And I think with this, we are over to why do we need quantum error correction and what are the noise sources that are different from classical to quantum.
Yeah, hi. I will be mostly talking about the quantum error correction and in terms of mostly the noise sources. And this is Hemanathan from University of Iceland. And I will just go through some first on the very basics of quantum bits and the quantum logic. So it's like, so in the classical bit, we mostly encode the information in the zeros and ones. And in the quantum, we have this ket0 and ket1s. And these are mostly represented on the block sphere. And the general state is like you have this psi, which is written in terms of it's a superposition state of ket0 and ket1s. And you for the logical operations, you have these unitary gates, and for the measurements, you do the projection on this using this different set of operation. And you take the probability of these projection operators, and you then get an outcome of it. Okay. So in terms of the hardware, like the realization of the quantum is mostly it's like you have a microwave cavity, and which is mostly like you have a resonator with equal spacing of frequencies, and then the superconducting Josephson junction is used for the qubit representation. And when basically it's like when you have this Josephson junction coupled with the cavity, the spacings will become unequal. This is the unharmonicity. And then this, the bottom n is equal to 0 and the 1 are the states which are the computational basis for quantum computing. And so in general, the Hamiltonian for the cavity is like this on the left-hand side, and on the for the whole qubit system, it is like coupled with the cavity is on the right side. So what are the different sources of errors which usually one notices when you do this quantum operation is like you have this decoherence error, which is like you have a qubit like and the qubit is going from can go from the state 1 to the state 0, and this is the energy decaying process. And there could be also a dephasing, which is like there is a loss of superposition states, the coherence in the superposition states. And you can also have a gate errors, like which is like it's an imperfect implementation of the quantum gates. And you have, like yesterday, you also learned about the state preparation and measurement errors, like uh, and then there could be a crosstalk, like when you have the circuit, you can have like errors coming because of encoding from different gates on from the different layers. And this also reduces the fidelity of operations. And then you also have this leakage errors. As in the previous slide, you have this like energy level representation. So in the leakage errors, like there could be kind of a transition into a higher energy states. Okay. And then you have this a couple of other noises or errors, like stray interactions, which is like when you have unintended couplings between the gate operations. And the other one is ideal errors. These ideal errors are like when you are not doing the operations on the qubits, and you if the qubits are just waiting for an operation to come, then it's like it can interact with the environment, and these are the ideal errors. And finally, you have also a noise coming from the electromagnetic interactions, and also from the like a cosmic microwave background. So how, like if you run a surface code, this is the recent work by the Google, and they ran this surface code with the 72 qubit processor with the distance 5 surface code. And this is how the error distribution is like for the surface code looks like. You have this control Z gates dominant, uh, and the whole control Z gate contributes to like 45%, and you have like a single qubit gate errors and the leakage errors, and like a reset, readout, and the data. If the data qubit is ideal, then you have like a 20% of the error is coming because it is just sitting for waiting for the operation to come. And then because the qubit starts decaying into the ground state, so you try to like do the operation. You have to do the operations beforehand. And then you have also other errors like control Z leakage and control Z crosstalks. And so to model these noise channels, you can generally go to this noisy quantum channels. Like basically, this is the general representation where you have two input channels and two output channels. It's like a 2 qubit to 2 qubit. And you can think, or else you can assume that E is the environment, and then you have a single qubit to the two outputs. And the examples of a noise effects is already mentioned, like a degradation of the quantum states, and reduction in the entanglement and decoherence, coherence, and significant impact of fidelity and performance. So to mostly to model these systems like open systems where the qubit is coupled with the environment. You go with the cross operators, and this gives you a general framework of handling this doing a modeling of these qubits when interacting with the environments. And so the density matrix, instead of using a wave function, you use the density matrix, and the density matrix evolution is written in this form. And you have a completeness condition for this. And these operators, we can use it for doing bit flip errors, phase flip errors, and different errors. So for suppose in the bit flip channel, so error, basically the zero state is going into the one state. So you have a noise, you try to model this thing like you have an identity matrix, and then you have error coming because of this p times the error x row x dagger, and the cross operators is written in this form. And similarly, you have this depolarization channel where it's like the qubit is randomized with a probability p, and here we assume that there is an equal probability for px is equal to py is equal to pz, and the effect of this channel is this represented by this, and the cross operators are equal given also. And you have also similarly for the amplitude defacing, where there is a loss in the energy dissipation process. And so now for the quantum error correction, you need to basically protect the quantum information against all these kind of noises and the decoherences. And so if you look into the steps, you have to like detect the errors and correct the errors and ensure for the long-term fault-tolerant quantum computation. So in the classical, just going one step back and looking at the classical bits, you have this 0 and 1 and 1 to 0, as Franz mentioned about this probability P. So similarly in the qubits, you have this kind of a different errors where you have a bit flip error, where when the ket0 is going to the ket1 and the ket1 going to the ket0, or you can also have a phase flip errors, or both as a bit and the phase flip errors. In addition to this, you can also have this continuous errors. And so for this continuous errors are analog actually inherently, and the idea is how can we correct this kind of continuous errors. So you can write any error in terms of this alpha 0 time plus with the relative phase, and this relative phase angle is like you can consider as infinitesimally small, and any error you can write in terms of this discrete Pauli errors with continuous coefficients. And here it is shown for a general error, and with written in terms of this Pauli error matrices. And yeah, the coefficients EI is actually could be infinitesimally small in principle. And now, how do you do this measurement? Like, how do you turn the measurements from the continuous to the discrete errors? So, suppose if you measure the error state using the operators mi, then the probability of that the state collapses is given in this form. So, this process collapses to the superposition and reduces the continuous coefficients into the discrete coefficients, like a discrete point. And now it's like, yeah, that's for this one. And let's go to the repetition code. So a key concept in error correction is like this adding redundancy. Like basically, it's like you try to, for suppose if you take in the classical bit representation, if you try for 1 0, you try to repeat this 0 into 3 bits. And this is a classical repetition code. Now the idea is, can you do the same thing for the quantum? Like, can you repeat this quantum? But the no cloning theorem tells that you can't do that, basically. And so what is there any other alternate for doing this kind of a copying? Or how do you transform the information which is encoded in a single qubit? So what we do in the quantum is like, basically it's like instead of copying the qubit, we copy the basis information. Basically, it's like you try to encode the information into multiple physical qubits, and it's like you transform the information during this. And yeah, so with this, you can actually correct qubit, entangled qubit information later, basically. So let us look how this, in the case of the repetition code. So in the repetition code, now let's assume that you have like a kind of a bit first, when there is no qubit was flipped, you have this kind of a projective measurement. And when the first qubit was flipped, then you can see that it is given by the P1. And for the second qubit was flipped, then it is in the P2. And similarly, for the third qubit was flipped, then it is like a P3. So these are like the projective measurements. And now, like if you reverse the thing, like since we know that which error occurred, we can now correct it. And this is how like the correction operators are. And since the measurement collapsed the state, so we need to use the ancillary qubits for syndrome measurements.
Can I just suggest that we have a quick question from the HackMD, which came up earlier.
Should I give back the mic then?
You can answer in the mic here if it's directed at you. So at what point or what stage in the development process should we consider implementing error correction for creating an algorithm?
So usually, hello. Yeah. So when you look at the the software stack, like basically it's like when you're looking at the quantum hardware, like you have a layer of a QPU, and then on the top of this, like you have when you are doing this readout measurement, like you try to detect if there are any errors in the readout measurement, and you do the decoding process to basically correct the if there is any error.
Okay. Yeah, I'm going to take over for a little bit now. I'm Delphine from University of Oslo. Okay, yeah. So I was saying I'm Delphine Mart from University of Oslo. So as Hemanaden was explaining, I'm going to talk a little bit more about the bit flip repetition code that he was talking about just now. So this is basically the circuit implementation for it. So like he was saying, in a quantum error correction, you have two problems to kind of take care of compared to classical error correction. One of them is the fact that you cannot copy quantum states, the no cloning theorem, which we solve by simply using, instead of copying states, you simply entangle qubits. So this is the way we do this encoding thing here, where if you have your state psi that you want to encode here, if it's a 0, since we use C naughts here, it's going to be 0, 0, 0. And if it's a 1, similarly, it's going to be 1, 1, 1. And then the other problem that we have is that measuring a quantum state collapses its state. So that if we want to keep doing computation after having detected errors and corrected them, we need to introduce these ancillary qubits here and do syndrome measurements on them instead of doing the syndrome measurement directly. So in this case, after the encoding, you may have some kind of noise happening. And then what you do is that you do exactly what Franz talked about, the classical error correcting codes. You do parity checks. So you check pairs of qubits and you check that they have that they are in the same state. So basically, if this first qubit here is 0 and the second one is 0, then you won't have a signal here. And similarly, if they're both 1, then in the first ancillary qubit you won't have a signal because you get 1 here, and then it flips back to 0 here. So you get 0 at the end of the measurement. And you do this for both pairs of qubits here, and that gives you a syndrome, much like for classical code. So for example, here if you have Pauli X, so bit flip error on the first qubit, then this is going to flip the first ancillary qubit here, and you get the syndrome 1, 0, from which you can deduce that the correction to apply is, well, exactly the error that happened, so X1. And then similarly, for if you get an x3 error, this one, the second qubit will be 1. So you get 0, 1, and you know that it's x3. And then if x2 error happens, then both ancilla qubits will be flipped. You get 1, 1 syndrome, and you correct with x2. Yeah. Now I'm going to talk about a little bit about the stabilizer formalism, which is a way to talk about quantum error correction codes. So stabilizer codes are a class of quantum error correcting codes that are defined by commuting sets of Pauli operators, which are called the stabilizer generators. So actually the repetition code that we just talked about is an example of a stabilizer code. So we need a little bit of math for that. So first of all, let's define the Pauli group, which is just a set of all, it's a group of all Pauli operators. So identity, Pauli X, Pauli Y, Pauli Z with the prefactors plus minus 1 and plus minus I. And actually it's enough to just consider X and Z together with the prefactors plus minus I, because Y is just equal to IXZ. And the reason that we are considering just the Pauli group is because any qubit unitary can be written as a linear combination of elements of the Pauli group. Then I also defined the group Gn as the n-fold tensor products of elements in G1, because we're going to need we're going to need to apply these to like many qubits. So as just as a notation, what we usually use is instead of writing this whole tensor product here, which takes up a lot of space, if we have Z operators applied to qubit 1 and qubit 3, for example, here we just write Z1s and 3, and we just omit the identity in the middle there. So this table as a group. So consider some subgroup S of Gn where all elements commute. So abelian subgroup. The stabilizer group is an abelian subgroup of the n-fold Pauli group. And then let the S be this should be 2 to the power of k. Sorry about that. Yeah, 2 to the power of k dimensional subspace of n qubit states defined by so S here is an element of Vs, and S psi equal +1 psi. So that means that psi is a +1 eigenstate of all states in S. So that actually defines the code space of your stabilizer, and this defines so the notation is nk with these brackets here. This defines the nk stabilizer codes, which encodes k logical qubits into n physical qubits. And we say that S is a stabilizer group of Vs, and grossly call Vs the code space stabilized by S. So let's go back to the example of 3-qubit repetition code, which is the 3-1 stabilizer code. And in this case, the stabilizer group generators are Z1, Z2, and Z2, Z3, which is just a choice. You could have you could choose different generators, but this is like the canonical choice. And then the code space is going to be all states which are linear combination of states 0, 0, 0, and 1, 1, 1. So how do we detect and correct states in stabilizer codes? So if some error G, which is in the Pauli group, occurs on our code state psi, since elements of Gn either commute or anti-commute, G will either commute or anti-commute with each stabilizer in S. If it anti-commutes with at least one stabilizer, we call it a detectable error. And if it commutes with all stabilizers and is not itself a stabilizer, it's a non-detectable error, which is actually just a logical operator. So let's go back to the example again of the 3-qubit repetition code. In this case, if you have error x1, like I showed on one of the circuit slides, error x1 is going to anti-commute with the first stabilizer generator, Z1, Z2. So x1 is a detectable error. But conversely, if you have the error x1, x2, x3, so if all 3 qubits are flipped, This actually commutes with both stabilizer generators. So it commutes with all stabilizers because you have here X2, Z2 anti-commute and then X3, Z3 anti-commute again, so it commutes. And same for the first stabilizer generator. So yeah, this three qubit flip is a non-detectable error. And actually it's the logical X, because if you have state 0, 0, 0 and you apply X1, X2, X3, it's going to be flipped to 1, 1, 1. So logical 1. So what you do to detect errors is you measure all the stabilizer generators on your logical state. And that gives you a syndrome that you then use to apply the corresponding correction, which is like exactly analogous to the classical parity checks that Franz talked about earlier. So if I go back quickly to the circuits that we saw earlier. Can I do that? Yes. This is exactly what we're doing here. So we're measuring on each of these ancilla qubits. Here we're measuring Z1, Z2, because we're measuring the first 2 qubits in basis Z. And here's Z2, Z3. And in the end, you get syndrome. So here Z1, Z2 lights up. So you yeah, on this one, Z1, Z2 lights up, so you correct with correction X1 here. Z2, Z3, and here both Z1, Z2, and Z2, Z3 light up, so you know that it's X2. Assuming that that errors only happen on 1 qubit, which is the most probable. Yeah, so I'm going to talk about a little bit about subtype of stabilizer codes. So actually, in general, stabilizer generators can have mixed elements. So you could have like X1, Z2, Z3, X4, for example, as a stabilizer, one of the stabilizer generators. But this type of code, which is Kalderberg-Schorstein code, are a nice type of stabilizer codes that are built by taking the parity check matrices HX and HZ of 2 classical codes, C1 and C2, to define the X and Z stabilizers respectively. So if you construct a code in this way, then your generators are thus only pure X or pure Z operators, which you're going to see a little bit more about in the hands-on session later. And that makes them kind of easier to deal with because they have like nice structure. And in this case, since you need to do syndrome measurements on not only Z stabilizers, but also X stabilizers. To measure a qubit in the X basis, you need to apply Hadamard transform to the qubit, since you have that HZH is equal to X. But you're going to see a little bit more about that in the hands-on session again. I'm going very quickly over this. So now we want to do filtering quantum computation with the CSS codes. So the nice thing, one of the nice things about CSS codes is that you can implement them. You can implement logical gates in a transversal way for all Clifford gates. Transversal gates, they are gates that can be written as a tensor product of gates inside each code block, and they're type of filtering gates. They're very nice that way. I'm going to talk a little bit more about that in the next slide. But yeah, so for example, to talk a little bit more about the CSS code, in some CSS codes, the C0 gate between logical qubit 1 and 2 can be implemented by applying a C0 gate between each homologous qubit of code blocks 1 and 2. So this is what you're seeing here on the figure on the side. You just entangle, you just apply C0 like between each pair of qubits on different blocks. And that's a fault tolerant way of doing it. So why is it fault tolerant? And why is another way not fault tolerant? So an operation is said to be fault tolerant if it does not increase the weight of an error, which is equal to the number of qubits that the error affects within one code block. The reason we do this is because we're correcting each code block independently, so that basically costs, if there's more than one error within one code block, then you're less likely to be able to correct it, as opposed to having one error in each code block. So the first circuit that you're seeing here is a non-fault tolerant implementation of C0 gates. I didn't draw it entirely, but you can just imagine like cascading C naughts on the whole 6 qubits here. So if you have an error here on the first qubit, then it's going to get transmitted through all these C naughts here. So that in the end, kind of all the qubits in each block get like infected by the error. Whereas if you have this transversal construction here, which implements the same thing, then the error is just going to get transmitted on the first qubit of the second block. So you just have error on the first qubit first block and the first qubit of the second block, and all the other ones are healthy, so to speak. And then when you do the correction, the error detection and correction, you just do a round on each block, and that's you can just correct both errors in one go. So that's why it's fault tolerant. So transversal gates are nice, but unfortunately we have this theorem that tells us, the Easton-Hill theorem, that tells us there is no non-trivial local error detecting quantum error correcting codes that admit a universal set of transversal gates. And that's kind of sad, but fortunately, the transversal construction is not the only fault tolerant construction that we can do. Yeah, so I guess I can hand it over to you. Jérôme is going to talk a bit about what it means to have universal quantum computing with logical qubits.
Thank you very much. And once again, while we transition to the next talk, let's open the room for questions.
Hi, I have a question about what happens if you have errors during your encoding and syndrome measurement. How does that affect your error correcting protocol?
Yeah. So you're totally right that happens. So here we're just talking about error correction. We kind of assume perfect model of like encoding and then NSLM measurement that you don't have. You won't have errors on like the construction part of your code, but that actually happens in real life. So what you do is you try to make them fault tolerant by doing like smart constructions or by having more robust qubits. And this is all part of fault tolerant, like how to make fault tolerant circuits. But here I was just like talking about the simple model of quantum error correction. But you're right that in reality it's more difficult, and people are like taking that into account. But yeah.
Okay.
I don't know if you want to say more about that.
In the lecture, we will also, or in the hands-on section, we will see how to encode fault-tolerantly logical qubit. And as you said, it's important that when we prepare the code state, that we don't spread already errors, because that's basically ruining all the effects that quantum error correction can have.
Thank you very much. There is another question in our shared workshop document, and it might be targeting Suhair. Yesterday, it was mentioned that sometimes the fastest way to deal with error spreading is asking the Helmi team to recalibrate the system. Can you explain to us what that is about?
Yeah, so that was a bit of a joke, honestly, obviously, but yes, oftentimes the best way of dealing or the best way of reducing error is honestly just to have a great calibration. And that's why, for example, queue lengths are so important, because I think I was talking with someone who mentioned that they were running jobs and they were in the queue for 6 hours, and by the time those 6 hours were over, the calibration had shifted, so all the optimizations were gone. So oftentimes it is best that when you run your circuit, you know exactly which calibration you're optimizing it for. So that's what it was about.
Makes sense. Thank you. Okay, anything else? If not, let's give the floor to Jérôme.
Thanks. I'm Jérôme Lenzen from VTT, the Technical Research Center in Finland. And yeah, I'll continue now with universal quantum computing with logical qubits. And then we will move on to the surface code and just talk about fault tolerance or fault tolerant quantum computing in general. So just to recap, we have a bunch of physical qubits that we entangle. That is what we call a logical qubit. And then we measure those parity checks expressed through stabilizers to basically detect errors. That's where we are currently at. And now when we have a logical qubit, we of course want to do quantum computing with it. So we need a set of gates that allow us to express our quantum algorithms on those logical qubits. And as Delphine has already started, we can easily find logical Hadamard, S gate, X gate, Z gate, and C naught gate. But one issue is that not all logical gates are efficiently or fault-tolerantly implementable through transversal applications. So for example, a Hadamard gate can be implemented by applying Hadamard on the physical qubits. But we have, for example, non-Clifford gates, which, for example, one instance of a non-Clifford gate are the T gates, is the T gate, which introduces a phase. And that one is required to obtain a universal gate set. And that cannot be implemented transversely. And there are schemes to actually do that T gate, to apply it on logical qubit, but those schemes are faulty and require careful analysis, which we will do later. So one idea how a T gate can be applied to a logical qubit is shown by the circuit down here, which uses quantum teleportation. So basically the psi-L is the logical qubit, with which we used during our quantum algorithm. And now we want to apply a T gate to our psi. And what we can do is prepare another logical qubit in the state 0, apply transversely the Hadamard gate, and then apply a faulty T gate, which I will explain later, and then basically entangle the two logical qubits and then teleport over our psi. And based on the measurement of psi, we can apply some corrections, and then we obtain this logical T gate. So we can quickly have a look at how that works. So we want to apply a T gate to an arbitrary logical qubit expressed by A0 plus B1. And we know that we need an ancilla qubit. And after we did the Hadamard gate, the T gate, and the C naught gate, what we get as a state is basically this entangled state here, where what we do then is basically measure the ancilla. And what we can see is when we measure 0, then the logical state psi will be in A0 plus B e to the power of I pi over 4, 1, which is exactly the application of the T gate on the logical qubit. And if we measure 1, then we basically have the same, but A and B are flipped. And what we can do is then apply this correction here as X, which will then prepare the correct state. And that's basically a construction to apply non-Clifford gates on logical qubits through teleportation. But as we'll discuss later, we need this faulty T gate, which cannot be implemented transversely on logical qubits. So keep this construction in mind. So, so far we have only talked about how we can detect errors, and that logical qubits allow us to detect errors by measuring ancillars. But we haven't really talked about why quantum error correction works. And there's this famous theorem called the threshold theorem that shows that when we can prepare or construct hardware that has a physical error rate that is below a certain threshold, and we then use a quantum code with a polynomial number of qubits overhead, then we can effectively exponentially suppress the error if the physical error rate is below a certain threshold. And that's basically why quantum error correction works and why Google and everyone else who's building quantum computers is interested in quantum error correction. Because if we can push the hardware error rates under this threshold, then we get this exponential suppression, and then we can basically keep our logical qubits alive indefinitely. And that's displayed here in the simulation. So on the x-axis, we have the physical error. On the y-axis, we have the logical error. So we are looking at a single qubit. And D expresses basically the number. It's a proxy for the number of physical qubits that we use in the logical qubit. And as we increase the number of physical qubits in the logical qubit, we can see that if we're below the threshold, so on the left side of this vertical dotted line, the error drops exponentially as we decrease the physical error rate. And that's basically the magic of quantum error correction, that if we can drop below the threshold, we get exponential suppression. Right, so I will now switch to the hands-on section. Any questions regarding the threshold theorem or like fault-tolerant quantum computing in general? Yes?
Thanks. It's been nice to hear about error correction coding. I'm a coding theorist, but in the classical sense, though. But how close are we to this threshold? Like, any idea?
Yeah, so the threshold is a function of which code we're using, what kind of noise is on our hardware, and later we'll see also what kind of decoder we are using. So the thing that basically looks at the syndromes and tries to find out if the logical qubit was flipped or not. Now, there are basically a gazillion models out there that give you different threshold numbers. But specifically for the surface code, which is the quantum error correcting code that Google tries to implement, we estimate that the threshold is at 1% physical error rate. So, but this physical error rate P can also be decomposed into all those error noise sources that Hamadan introduced this morning. So we have leakage, we have idling errors. So you really need to very carefully analyze what it means to have a physical error rate of P. So currently it's roughly 1%. So our hardware is getting there, but we also need to scale. So if we look, for example, if we are below the threshold, but we are only at D equals 7, then we get only a slight suppression of the error. And that might not be sufficient to do quantum computing on our logical qubits. Actually, it's estimated that we need a logical error rate of 10 to the power of minus 10. So you can see on this slide, we don't even see it on the y-axis. And that means that we might need 10,000, a million physical qubits for a single logical qubit. But in the hands-on, you will also estimate the surface code threshold and get a better feeling.
Thanks.
Any other questions? Great. I need to swap laptops. No, actually, I prepared everything on this one. Let's see. Okay, so I hope everyone has access to Lumi and has already started their Jupyter Notebook session. If not, quick reminder, so you can go to lumi.csc.fi, you log in, and then you basically request a Jupyter Notebook, and it's the same procedure as yesterday, so nothing changed. I guess some of you have not done that yet, so I'll just wait and go slowly. So you go to lumi.csc.fi, you click on Go to Login, you authenticate. This was skipped now, and then you click on Jupyter for Courses. Takes a long time to load for some reason. But when you load this page, you should get sorry about that. Yeah, you should get to this page here. And this page is basically allows you to select a reservation. So you should select Quantum Autumn School, a project, and then just click Launch. And it should give you a Jupyter Notebook. When the Jupyter Notebook is scheduled, you can click here to connect on Connect to Jupyter, and that will open a notebook like that one that you can see here. So maybe you can give me a thumbs up if at least one or two of you have already opened the Jupyter Notebook. Yeah, sorry. So you should open the CSC code Steen Jupyter notebook, which you can find under content/notebooks. Yeah. Did anyone manage to open the Jupyter notebook? All right. So Lumi is tired this morning. Otherwise, if you don't want to execute the code but follow along, you can go to the sorry, Zoom is to the ENCCS GitHub page, and then you can click on the course material webpage, and there you should also see under day 2 the tutorial fault-tolerant quantum computing with CSS codes. And that's basically displaying the same notebook as HTML, but you cannot, so you can see everything, but you cannot execute. So that's also fine if you just want to follow along. And let's start, and I hope you can help each other out. So I'll start slowly. So we have now many concepts. So we have the stabilizers, which we want to get familiar with. We have, in general, quantum error correcting code. So we now really want to understand what does it mean to implement such a code on the circuit level. What does it mean to basically prepare a logical qubit? So we had already that question, like, how can we actually prepare fault-tolerantly a logical qubit? And then, yeah, how do we do quantum computing? How do we apply logical gates? So a logical X, a logical C naught on our qubits. And later, there's a section in the notebook that shows how quantum error correction is actually done. It's quite a long notebook, so I would recommend that you look at that at this part on your own. There's one paper by Quantinuum, which is explaining all the steps, and I basically re-implemented them. Yeah, which is a good lesson if you really want to understand what's going on the hardware-software level. Okay, so the code that we're today looking at in this notebook is called the Steen code. Was introduced by Andrew Steen in 1996, so it's a quite old code. Given that the field of quantum error correction is quite young, I guess we have mathematicians here that have much older codes. And the Steen code is a 713 stabilizer code. So just to repeat what that means, we have 7 physical qubits, and we encode them to form one logical qubit. And the 3, we haven't really talked about it, but it's the so-called code distance. And it tells you how many physical errors we can correct reliably at the same time on this code. And there's a theorem that tells you that if we had to have a code distance of d equal 3, for example, in the Steen code, then we can correct up to d minus 1/2 errors, which in our case is exactly 1 error. So we entangle 7 qubits, and we can efficiently decode exactly 1 error. So yeah, it's not great, but it's also not terrible. So let's start a little bit talking about the code construction. There will be some math involved, but yeah, I hope it's not scaring you off. So Franz this morning presented the linear codes, so classical codes, and they can be represented using a parity check matrix, which basically tells you which parities you have to compute to verify that a binary string is actually a valid code word. So basically it's each code word X that is a valid code word is in the kernel of this parity matrix. So it's mapped to 0 for the parity matrix H. And now Delphine introduced the so-called CSS codes that have a very nice structure. They can be represented by 2 parity check matrices, H1, H2, which represent basically which stabilizers we are measuring. And we are measuring exactly 2 types of stabilizers, X-type stabilizers and Z-type stabilizers. And then each row of those parity check matrices define a stabilizer. So for example, if we have in the ith row of HX, we have 1, 0, 0, 1. that translates to, or corresponds to a stabilizer x1, x4, which means we're checking for z errors on qubit 1 and qubit 4. And there's basically one condition so that a parity check matrix can actually express a stabilizer code, and that is that all the rows of hx and hz must commute. So for the Steen code, we have a special condition, and that is that the stabilizers for x-type and z-type are exactly the same. So we can express the Steen code by a single parity check matrix, which is displayed here. And well, we learned now how to interpret this. So we have 7 qubits, and the first stabilizer will basically check the first 4 qubits. So the stabilizer is x1, x2, x3, x4, and z1, z2, z3, z4. And then the rest of the stabilizers follow the same construction. Now, given those stabilizers, we can jump into the first exercise, and that is to think a little bit, how is a logical state actually expressed as a ket vector? So we know that one of the constraints is that given a valid stabilizer state, it must be the simultaneous eigen vector of all stabilizers. So S phi must map to +1 phi. And now your task is to think a little bit, how could such psi look like? So please take some time to think about this. Maybe I can give you a hint on how to start. So let's assume we have, for example, the state 0, 0, we have 4 zeros, and let's say 1, 1. Then if we apply the first stabilizer, which is x, 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 y, 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 then this would map to 1, 1, 1, 1, 1, 1, 1. So if we have a valid, if we want to find a valid psi, then we need at least the superposition of the two. So the psi will be a superposition of 8 binary strings. So I'll give you 2 minutes to think a little bit about this, and then I'll show you an example of a state. And it's a good idea to only think in terms of binary strings and not in plus minus states. This makes things very complicated. Okay, I'll show you the solution. So yeah, as I mentioned, we need a superposition because a single state consisting of a binary string will necessarily be flipped by at least one of the stabilizers. So we need a superposition. And then we just need to make sure that basically if we for example, if we start with the first binary strings, all zeros, and we apply the first stabilizer, x1, x2, x3, x4, then we obtain the second string in the psi state, which is 1, 1, 1, 1, 0, 0. And then we can basically continue by taking the second stabilizer, apply it to 0, and then we obtain the third binary string and so on until we have tested all combinations. And in the end, we noticed that we are basically cycling through those 8 binary strings. And there's even easier way to generate this by just thinking in terms of independent vectors and then basically representing all linear combinations of the parity check matrix rows. So it's a little bit of math involved. So to go a little bit away from the mathematics, because that's usually confusing, let's find a language to visualize stabilizer codes. And we have seen that we have 3 x-type stabilizers and 3 z-type stabilizers, and they measure particular physical qubits. So what we usually do is we think in terms of so-called plaquettes, where each plaquette denotes one stabilizer. And then you can think of the ancilla qubit measuring the stabilizer as in the middle of the plaquette. So we entangle all the 4 qubits with the ancilla qubit in the middle. And then when we think of arbitrary stabilizer codes, we can basically draw a nice 3D, 4D, okay, maybe not a nice 4D diagram, but at least in 2D and 3D, we can express those stabilizer codes as nice geometrical structures. And we can just think about basically how those look like and what that means for the logical operators later. So the Steen code is basically a triangle with 3 faces, and each face is measured by 2 stabilizers, one X-type, one Z-type stabilizer. Any questions so far? Okay, great. So, of course, we want to simulate the Steen code. So we will use a tool called STIM, which is currently being developed by Google. It's heavily used in the quantum error correction community to simulate quantum error correcting codes, to simulate the properties, and to evaluate quantum decoders. So it's a really important tool, and these days when you publish large-scale experiments, what you usually do is also you publish a STIM code alongside your paper. So I'll try to introduce it and basically present the most important objects in STIM. So we have 3 really important objects. That's the Pauli strings, just a representation, a software representation of the Pauli operators, and then we have a tableau and a circuit. So let's start with the Pauli strings. So as Delphine introduced, the Pauli strings is just a tensor product of single qubit Paulis. And we usually omit identities and use indices to make clear that we know to which qubit we are applying the Pauli operator. And of course, in software, we in the end just operate on binary strings. So we now need to map each Pauli to a binary representation. And we can use a simple encoding. So basically, we have 4 Paulis, so we need 2 bits to represent them. So I will be represented by 2 zeros, X by 1 0, Z by 0 1, and Y by 1 1. And since we have at least 2 mathematicians here in the audience, that's a group homomorphism from the group of Paulis to the 2-dimensional Z2 space or group. And now how can we do Pauli multiplications in software? So if we want to multiply A and B, which are Paulis, so for example X and Y here, we encode them, translate them to the binary strings, and then just do bitwise XOR, which is extremely efficient on CPUs. And then we get the result, which is X times Y is Z, ignoring the phase. And now you can basically load the first cell. So here we define 2 Pauli strings, plus XX, plus ZZ. And basically the cell shows you what kind of operations are supported. So we can multiply the strings, we can concatenate them, and we can do checks like, for example, do 2 Pauli strings commute. So rather simple. Next, I'm going to just go over the tableau. It's a little bit too complicated to go into the details, but basically if you want to efficiently simulate quantum error correcting codes, you will need to efficiently simulate stabilizer circuits. And stabilizer circuits are circuits that only use Clifford gates, because Clifford gates map Pauli strings to Pauli strings. So for example, for Clifford operator C, if we have a Pauli string P, then the C, which could be, for example, Hadamard gate or C0, will map the Pauli string to CP, C dagger, which is basically a conjugation operator. And since we are mapping Paulis to Paulis, and we can express quantum error correcting codes as through stabilizer generators, what we only need to do during the execution of stabilizer circuits is to track how these stabilizers generators change over time. So basically, if we have a bunch of stabilizers, for example, for our Steen code, and we hit a C0 gate, then we just conjugate the C0 with all our generators, obtain a new set of stabilizers, and that tells us how the new state is generated after applying the unitary. So just to show you, there in STIM, there's this Tableau simulator object, and it internally basically keeps track of stabilizers, and you can apply operations on it. So you can, for example, apply a Hadamard gate followed by 2 C0s, and then do a measurement of the Tableau. So that's the famous GHZ state. So, and as expected here, we get 3 times the same value or measurement. And if we execute this multiple times, we get always the same value for all 3 single qubit measurements, which is what we expect. Since STIM's Tableau is really heavily optimized to really run large-scale code distance, surface codes with many, many physical qubits, if you look at the internals of the STIM Tableau simulator, it's quite complicated. So what I recommend is reading the original paper that introduced stabilizer simulators by Aronson and Gottesman, called Improved Simulation of Stabilizer Circuits. And that's a really nice paper that goes through how to basically implement your own stabilizer simulator. I think in C it's like 400 lines of code, and with Python it's maybe even easier. Okay, and then there's a third object in STIM, which is called the circuit. And I think for us it's the easiest API to understand. It mimics basically what Qiskit and Cirq provide to the end user. So you can basically apply gates to a circuit, and then you have different ways of visualizing the circuit using the diagram function. So for example, you can use text, or you can generate an SVG, and then you get basically the Bell state preparation circuit that we also used in the stabilizer Tableau. And next, what we can do is compile a sampler, which will basically run a simulation of the circuit and return some shots as a NumPy array. So here again, we see that all 3 qubits have always the same measurement. And what we can also do is use our Tableau simulator to run the same circuit. And in the Tableau simulator, we have always access to all measurements through the measurement record. So maybe to recap, we have Pauli strings, which is a representation of in software of Pauli operators. We have the Tableau simulator, which is basically the atomic thing that executes circuits. And then we can also define circuits, which we can then give to the Tableau simulator, and it will execute it. So this way we can easily simulate any quantum error correcting code using STIM. Okay, so back to the STEAM code. So we know from the lectures that there's one condition for the quantum error correcting code, and that is that a valid code state is the simultaneous eigenvector of all our stabilizer generators. And we have 7 qubits and 6 stabilizer generators, meaning, like intuitively we think about it, if you have 6 stabilizers that impose a constraint on your 7 qubits, then there's basically 1 degree of freedom left. And that degree of freedom is actually what allows you to implement a single logical qubit. So that's basically the idea behind putting those constraints on your quantum states. So it can be shown that if you have m stabilizers and n qubits, and the number of stabilizer generators is usually always lower than the number of qubits, then the number of logical qubits in your stabilizer code is k equal n minus m. So we have 7 qubits, 6 stabilizers, so 7 minus 6 is 1. And now, since we only briefly touched upon the logical operators, I quickly want to go through it. So a logical operator should always return a valid code word. That's like our first assumption, and that must hold. So that basically means that if we find the logical operator OL and we apply it on a logical state or a valid code word, then since the valid code word is stabilized by S, we can just inject this S and nothing happens. It's equal. And that means that OLS So applying the logical operator to any of the stabilizers must also be a stabilizer. So that's basically what we find. So if we conjugate or apply any logical operator to a stabilizer, then we will get another stabilizer back. So what about the logical operators of the Steen code? So here again, I printed all the stabilizer generators. And what we can find if we do the math is that the X5, X6, X7 is one logical operator, and Z5, Z6, Z7 is another logical operator. And your first task is now to basically verify that. And you can verify that by basically seeing that if you apply this logical operator to the set of stabilizer generators, that you get the same set of stabilizer generators back. And that's what we do in exercise 2. So I'll give you a moment to have a look at exercise 2. And do you have any questions so far? I hope I'm not scaring you off with all the math.
The tableau formalism was based on Clifford circuits, right?
Exactly, yes.
So in case we use like a unitary circuit that is not composed only by Clifford gates, this is supposed like how it should change like the formalism?
So basically if you introduce a non-Clifford gate, then you would map the stabilizers are all Pauli strings. You would in the worst case, map your Pauli string to something that isn't a Pauli string. So you cannot represent it through a tableau. And that's usually what we try to avoid in a quantum error correcting code. We always want to express it through Clifford circuits, since we only need to measure Pauli strings. And so there's no need basically for applying non-Clifford gates.
But in a real algorithm, usually are the non-Clifford gates the interesting one? No?
That's true. But for simple experiments such as quantum memories, where you basically just prepare a logical qubit, you apply noise on it, and you correct it, there's no need to apply logical operators. And there we don't care so much. So STIM for now is designed to basically do those quantum memory experiments, but they're already working on basically simulating non-Clifford gates, but then you need to go back to Monte Carlo methods.
Okay.
So the complexity explodes basically.
Yeah.
And the best stabilizer simulators that support T-gates can, I think, simulate up to 60 T-gates.
Okay.
Which is not by far not enough to do any useful computation.
Okay, thank you.
And that's also basically where the power of quantum computing comes from, because assuming you could efficiently simulate T-gates, then you could simulate any quantum algorithm, and then, then you're done. You don't need to build quantum computers anymore. You can just simulate them. Anu.
Yes, I probably get lost with the setting of this. But I mean, if you have a quantum circuit,
yes,
can you somehow improve it with this? And how do you apply it?
Yeah, thanks. So the basic idea is that we have a quantum circuit and we have noisy qubits. So if you execute it on hardware, you will most likely get noisy results. So through the threshold theorem, we know that we can get exponential suppression of errors if we use logical qubits and decode the error fast enough. So our hope is that by replacing the physical qubits in our circuit through logical qubits, and then execute the algorithm on the logical qubits, that we get an exponential suppression of the error, which will then actually result in noiseless measurements. That's basically our setting. And here in this particular notebook, we are looking at the Steen code, which is a small error correcting code. It can only detect 3 errors and correct up to 1 error. But later we will look at larger codes, which allow us to correct and detect much more errors. And then you really get this benefit from quantum error correcting codes. But already for those small codes, it was shown that we get a nice suppression up to, I think, 800 times. that was recently shown by Quantinuum preparing a GHZ state on an ion trap machine. Okay, so to not spend too much time on this, I'll show the solution here. So, oh, sorry, Zoe, please go.
Yeah, so as far as I'm aware, there's some types of error correction codes that you can concatenate and scale them. So our CSS codes specifically, can you scale the Steen code, for example?
The Steen code cannot be concatenated, but what you could do is use the Steen code as a basis and then apply the Steen code again on your logical qubits. So you can basically, you get this inception moment where you encode your encoding. But the surface code is basically, which we will look at later, is a code that you can just scale. And you don't need this encoding and encoding. And that's where also the threshold theorem kicks in. As you grow the size of your code, you are able to detect more errors and efficiently suppress it.
Yeah, so that's what I was referring to with concatenating. I guess the term isn't official, but...
it is official. It's used in proofs, for example, for the threshold theorem.
Oh, okay. Thank you.
Okay, so what were we supposed to do? We were supposed to show that the logical operators do not change the state of stabilizer generators. And what I did here is I provided you with a list of the Steen stabilizers or the generators of the Steen stabilizers. And the first step that you need to do is to basically add the logical operators here as Pauli strings. So log x is basically 3x on x5, xx, and x7. And then you basically apply the logical operators on each of the Pauli strings by conjugating them. And when we execute this, we can see that it returns exactly the set of stabilizers. So for example, here we see, so basically the first list of stabilizers is after conjugating them with the logical X. And we can see that the first stabilizer corresponds to exactly the first stabilizer that we had in the original set. So the stabilizers are not changed by the logical operators. So this means that the two logical operators that I gave you are actually the logical operators of the Steen code. And then also importantly is that those, so I denoted them as logical X and Z, so they need to anti-commute if we want to really call them logical X and logical Z. Otherwise, they're just some random logical operators that might, in the worst case, even be equivalent. So what we do is we check that they commute, and they actually don't commute, so they anti-commute. And that means their actual, at least regarding the algebraic properties, they represent Pauli X, Pauli Z on logical qubits. All right, so now the next step that we need to do is to understand that there's an equivalence class for logical operators. So maybe to scroll up, if we have a logical operator and we apply a stabilizer on the logical operator, then this represents the same logical operator. So basically, logical operators are equivalent modulus the stabilizers. And that's basically the exercise that you're supposed to do in the second step. So if you apply any of the stabilizer generators onto your logical operators, you obtain different equivalent versions of the logical operators. So feel free to take basically any of the Pauli strings here and multiply them with the Pauli string here that represents the first logical operator, and you will get equivalent logical operators. To save time, I will just show you some of the logical operators. So here on the right, we can see, on the left, we can see the first logical operators, which is applied to qubits 5, 6, and 7. And then if we, for example, multiply this logical operator with the green plaquette, consisting of X operators on qubits 3, 6, 4, and 7, then basically X, the two X down here, are transported up here. And those are basically equivalent operators in our Steen code. What we then can do is apply the red square to our second equivalent logical operator, and that basically moves up the Pauli X operators to the other edge of the triangle. And that's another logical operator. And if we think about this, this makes sense because we spread our logical qubit over many physical qubits and entangled them. So it wouldn't make sense if we just, if a logical operator could just be expressed by applying it on 3 physical qubits at a fixed location. So the logical operators must be applicable on any parts of the code with some restrictions. I hope you recovered a little bit from all the math, because I will throw a little bit more at you, and then hopefully we get to a point where we can just do quantum computing and yeah, forget about all the stabilizers and whatnot. So maybe to recap, we have 7 entangled qubits which form the Stein code. We have learned that logical operators are represented as basically 3 single Pauli operators on 3 of the 7 qubits. We understand that they are logically equivalent logical operators, and that makes sense because if we would have fixed a logical operator on a certain qubit subset, that would be somehow strange, because why would the code then protect? So now the final thing that we need is like the other logical gates. So for example, Hadamard or CNOT, and then we can, for example, implement a logical Bell state. So since we are running a bit short of time, I will just show you the solution for the last exercise, and that is to show that a Hadamard gate can be, a logical Hadamard gate can be implemented by applying single Hadamard gates on each of the physical qubits. And we can verify that again by just showing that the logical Hadamard operator maps stabilizers to stabilizers, so they are not changed. That's always something that we need to check. And then if we really implemented a logical Hadamard, it would map the logical X operator to the logical Z and vice versa. And that's basically what you could do with pen and paper, or we can just look at the solution. So what we know is when we apply a Hadamard gate to X, it becomes a Pauli Z. And since the logical X consists only of identity and X, when we have identity, the 2 Hadamard gates, since we conjugate, cancel out. And if we hit an X, it flips to Z. So apparently we're mapping the logical X to logical Z and vice versa. So we found a Hadamard gate. And the same can be done for the S gate. Okay. So at the beginning of the lecture, someone asked, what about state preparation? So how do we go from having a bunch of physical qubits to having a correctly initialized logical state? And well, naively, we could say, hey, just prepare everything in 0. Might be correct. But if we think about our stabilizers, for example, X, 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 X on the first 4 qubits, that's definitely not stabilizing the all 0 string. So that's not going to work. And in general, state initialization is one of the more complicated topics in quantum error correction, because you really want to make sure that you prepare a state that is a simultaneous eigen state of all stabilizers. So what you can always do is to basically just measure all your stabilizers. And since they commute, you can do that in any way using ancilla qubits. And then you get a valid code state. But measuring all stabilizers in a sequence is quite costly in terms of entangling gates and difficult to do fault tolerantly. Further down in the notebook, there is an example of how that can be done. So basically, for each stabilizer, you need 4 entangling gates, because each stabilizer has a support on 4 qubits, because it checks 4 qubits. And so we have 6 stabilizers, and for each stabilizer, we need 4 CNOTs. So we would in total need 24 CNOT gates just to do the measurement of all stabilizers. But that's not ideal because CZ gates usually introduce a lot of noise into our quantum circuit. So as I mentioned, there's a lot of research on how to do this fault-tolerantly and fast. And there's one scheme by Goto, which I'm just going to present and not prove that it's correct. So we have this function here that takes an index for a logical qubit and then just applies the scheme. It's a bunch of C nodes which measure all the X stabilizers in parallel. And then at the end, use an ancilla to measure the logical Pauli Z. It's basically the idea of the scheme. So we have now a function that can encode a logical qubit, and we can print it in STIM. It looks basically like this. So we have one ancilla qubit at the bottom, and then our 7 physical qubits of the Steen code. And we can see at the end, we are measuring qubit 2, 4, qubit 2, 4, and 6, which correspond to a logical Z. We entangle it with the ancilla and measure it, and that basically project it to the eigenspace of the logical Z operator. So that's correct, at least that's proven by Goto, and we can also check this quite easily in STIM by just passing the circuit or transforming the circuit into a tableau. So that's something that STIM can do, and then print the stabilizers. So what we can see here, the first stabilizer is the 4x. So that seems to be correct. We'll skip the Z stabilizers. The second X is also correct. And the third X is also correct. So at least this circuit is preparing a state that fulfills the condition that the state, so if we start in 0, the state will be stabilized by the 3x stabilizers. And now by measuring the logical Z, we also ensure we have a condition on whether it's stabilized by the Z-type stabilizers. And we don't even need to correctly prepare an eigenstate for all the Z-type stabilizers. We can just later correct any error that occurred during the state preparation. So we can ignore basically the Z-type stabilizers. That's something that is shown in the paper, and we don't need to think about it today. So now we will jump into implementing really fault-tolerant quantum computing. So we will first define 2 helper functions. The first is measure the logical qubits. So what it simply does is it measures all physical qubits of the Steen code. And again, we have a logical qubit index just in preparation if we later want to measure multiple logical qubits. And then we have another function, sample from circuit, so we can give it an arbitrary circuit and it will basically sample a few shots from the circuit. So now we can basically, in the next exercise, put this all together and for the first time measure logical Z on our encoded circuit. Since we're running a little bit short on time, I will just show you the solution. So you would start with an empty STIM circuit with all qubits initialized to physical 0. And what we then do is we apply our encoding circuit to the empty circuit and then measure all the physical qubits destructively. Then we pass it to our sampler, which will return some shots. And now the question is, how do we actually compute the observable given our physical measurements, the measurements of the physical qubits, while we can just XOR the results for 5, 6, 7, mimicking a logical Z measurement. So let's check. If our Goto encoding circuit is correct, we would always measure logical 0. And we can already see that's the case. So we measured 10 times 0 because we ran 10 shots. And I also mentioned that we have an ancilla qubit that we use to basically measure logical Z. And this ancilla is also a flag for any state preparation errors. So it can be shown that if this is not 0, then an error happened. And well, in the absence of any noise, this will of course also always be 0. So that seems to be okay. Next, we would like to prepare our logical qubit in different bases. And here our logical qubit operators that we identified come into play. So what you can simply do is define a function that you pass basically the string, which gate you want to apply. So it could be Z, X, Hadamard, or S, the 4 logical operators that we identified, and then basically on which logical qubit you want to apply it. And I'll show you the solution here. So again, if we want to apply a Z, a logical Z, we apply physical Z's on qubits 5, 6, and 7. STIM indices always start with 0. For X, the logical X, we do the same, but this time with Pauli X. And then we showed that a Hadamard gate is basically applying Hadamards on all 7 physical qubits. And same for the S and S dagger gate. And then I have another helper function, which is not super important, but basically we can pass a Pauli string, define it, and then it will prepare the logical qubit as an eigenstate of this Pauli string. But that's not used in the next few cells. So now let's put this to a test. So here again, we prepare a logical 0, and then we apply a logical X gate and measure our qubit, and what we expect is all 1s. And if we execute this, we can see we get all 1s. Now I'm using my prepare stabilizer eigenstate. So the stabilizer for -Z is the 1 state, because if you apply Z to 1, you get -1, and then minus cancels out, so you get 1. So what we should measure here is 1s. And then finally, we can also do, for example, a logical X by applying H, Z, H. And that's also correct. So now we have shown that the logical operators that we identified at the beginning are all correct, and they also work on a circuit level. What we also usually want to do in quantum computing is to measure in different bases. So I also have a helper function for that. So usually we can only do measurements in the computational Z basis. That's basically a hardware, not a hardware limitation, but it's basically fixed in the hardware. And so if we want to measure in a different basis, we can, for example, apply rotations before measurement to change the frame of reference and then measure in a different basis. So for example, here I showed how to measure in the X basis by applying Hadamard gates before the measurement. And this function basically applies the right rotations before doing the measurements. So for example, if we prepare our state as an eigenstate of X, so plus state, and we measure, we get 0, 1, 0, 0, 0, 1, 0, 1, which indicates that we correctly prepared the plus state, because if you measure in the Z basis, you should get 50% of your states in 0, and the other 50% roughly in state 1. In this case, we didn't apply we didn't prepare the logical qubit in state plus, but we measure in the X basis, and that's basically the same procedure. And then you should get basically 50% in 0, 50% in 1. Okay, so now we are slowly coming to the end of this notebook. So now we really have all the tools to do fault-tolerant quantum computing. We can apply single qubit rotations on our logical qubit. And the thing that Delphine mentioned is that since the Steen code is a CSS code, we can implement the C0 transversely. And that means that we can apply basically pairwise C0s between the physical qubits of 2 logical qubits. And that will implement correctly a logical C0. So in this section, we will prepare a logical GHZ state on 2 logical Steen codes, basically. And in total, instead of 2 physical qubits, we will use 16 physical qubits. So there we already get a feeling for the overhead that is introduced through quantum error correction. So let's start by preparing two logical zero states. And here for the first time we use this index to make sure that STIM correctly shifts the qubit indices. If we look at the circuit, we again use the Goto encoding, and I think my session just stopped. No, it didn't. Nice. So if we look at the circuit, the upper part basically encodes the first logical qubit, and then the second part encodes the second logical qubit, and we know that from the previous cells that this construction is correct. So we're good to go. And now we can implement a function that basically does pairwise C-naughts between physical qubits at the same position in the two different logical qubits. So that's basically this function. And now to really test if we actually implemented a C-naught, I will flip the first qubit before applying our logical C-naught, and then apply the logical C-naught. And the circuit looks like this. Encoding, then the 3x represent the logical X operator, and then we do the transversal C-naught and then measure all physical qubits to check if we correctly prepared logical C-naught. And what we would expect is that if we flip the first qubit and then apply a C-naught, that we measure both logical qubits in 1-1. So let's sample from the circuit, construct correctly the logical Z measurements, and what we see is exactly 1-1 for all 10 shots. So now we can even entangle our logical qubits, and we can basically simulate any Clifford circuit with logical qubits. And now we can do the same steps again, but this time we prepare our first qubit and with the logical Hadamard, and that will basically implement a logical Bell state. The circuit looks like this, so we can now see that we are transversely applying 7 physical Hadamard gates to our first logical qubit. And if we measure this state, basically we would expect that 50% of the shots are in logical 0 and 50% of the shots are in logical 1, and that the qubits always have the same measurement result, because now the measurements are correlated. So if we do that, we can see that that's exactly the case. So it seems that roughly, so I ran here on 20 shots, that roughly half of the shots are in one state, the other half in 0, and we have the correct measurement statistic between the two logical qubits. Okay, so that brings us to the end of the Steencode simulation. Below there's a nice section on how Quantinuum did quantum error correction on the Steencode. It introduces how to inject noise into our circuits and really analyze how we can detect errors. So if you have time, please have a look. It also introduces basically how to decode errors, how to identify them, and what kind of types of errors we can detect and correct with the Steencode. Any questions regarding the content up to this? Okay, nice. I think the main work is done after you define the logical operators. It's rather straightforward to just apply them and show that we correctly prepare Bell state. So let's go back to the lecture. Stop sharing here and switch laptops. Okay, so now we have a good understanding of what stabilizer codes are, and now we will jump into the surface code, which is, I would say, one of the most widely studied quantum error correcting codes. It can detect and correct all kinds of errors. So it's a real fault-tolerant quantum code. And it's basically the basis for future fault-tolerant quantum architectures. So it's a code that really should be understood and studied. So the surface code was introduced by Kitaev, 1997, so it's a rather old code. And back then, he basically studied so-called topological quantum codes, which I will not cover today, but it's a very interesting class of codes. It belongs to the class of CSS codes and comes with all the goodies, such as transversal CNOTs. And basically, the surface code has data qubits, which are arranged on a lattice. And interspersed between the data qubits, we have ancilla qubits, which measure two types of parity checks. So the blue ancilla qubits, they measure for Pauli Z errors on the neighboring 4 data qubits. And the red ancilla qubits, they measure for Pauli X errors on the neighboring 4 data qubits. So if we change perspective and we think about a single white circle, for example, the one in the middle, then this one is checked by exactly 4 different ancillars, 4 different errors. But of course, we are not only checking a single qubit, we are always checking a quartet of 4 physical qubits, because checking a single qubit would destructively destroy the quantum state, which we don't want to do. All right, and this is a very nice quantum code for superconducting devices, because it only requires planar graph connectivity. And if you think about superconducting chips, usually the transmons are already aligned on a plane. And then if you basically align them on a lattice, like shown here, you can very naturally implement such a surface code without doing costly swap gates. And there was the question at the beginning, what is the currently best threshold? And we assume that it's roughly 1% for the surface code. All right, so just a recap of what I said before. We have 2 types of checks for Pauli X and Pauli Z type errors. We don't need to take into account Y errors because they decompose into X and Z. And basically, here we show or indicate how the circuit would look like. And the numbers tell you in which order we have to entangle our data qubits with the ancilla qubit to avoid so-called hook errors. So if we go back and we think about extracting in parallel all the syndrome measurements, what could happen is that if one of the ancilla qubits is faulty and we entangle it with our data qubits, we start spreading errors. And if we execute basically the wrong sequence of CNOT gates, we don't pay attention in which order we execute them, then we could, by a simple syndrome measurement, spread errors across the whole surface. So there's basically the sequence that is run in parallel on X and Z type ancillas that we always need to follow to avoid spreading errors and to basically implement fault-tolerant syndrome measurement. Just to recap, because we at the beginning talked about detectable and undetectable errors. So a detectable error is an error that anti-commutes with our stabilizers. An example would be a single qubit error on a data qubit. And undetectable errors are basically product of stabilizers or logical operators. So undetectable errors, if we have an undetectable error, it doesn't mean that we're actually flipping the quantum information in our logical qubit. It can also mean that basically nothing happens. And that's when we accidentally apply a stabilizer. And the beauty of the surface code is that finally we can leave all the math behind and just think in terms of nice chains. And I will show you how that looks like. So let's start with detectable errors. So here's an example of what happens when 3 Z errors occur on data qubits 10, 11, and 17. Now, if we start at 10 and 11, we see that this could be detected by ancilla 1, the blue one. But since it's measuring parities, and we have 2 Z errors, it won't be detected. So then we continue, and we see that 4 could also, for example, detect the errors on 11 and 17. Again, we measure parities, undetectable. But at the end of the chain, the ancilla qubit number 8 will catch basically the presence of errors because, yeah, well, we measure again parities and we only have one Z error. So that's basically flagged. And we can make this, so on the surface code, basically any detectable error can manifest as a chain, which is beautiful because in the end, we don't need to think about single errors anymore. We just think about chains. And if a chain ends up in the interior of the surface, then we will always detect its ends. So the start of the chain and the end of the chain. Here I showed an equivalent error chain. So the same ancilla is basically flagging the end of the chain, but this time only a Z error happened on data qubits 23 and data qubit 24. So we can already see that we also don't really care what kind of chain caused the error. We just basically want to detect the presence of such chains. Okay, then how do stabilizer errors look like? So undetectable errors. So any product of stabilizers will commute with all stabilizers, so undetectable. And for example, the loop around ancilla qubit 3 is such an example of a stabilizer. So on qubit 1, 2, 6, and 7. And basically, stabilizer or error chains that form a stabilizer are expressed on the surface code as loops. So chains that are closed. So we have now two types of errors: detectable, open-ended chains, and then undetectable loops. And then we have a third type of undetectable error, and that are the logical gates. And logical gates in the surface code always connect opposite borders. So for example, here we have the logical X, which is basically a Pauli X on the straight line between the top and the bottom boundary of the surface code. And we can really go through it. Ancilla 13 cannot catch the error on 2.7. Ancilla 16 cannot catch the error on 7.12. Ancilla 19 cannot catch the error on 12.17. And then at the end of the chain, Ancilla 22 cannot catch 17 and 22. So basically, when we connect opposite borders, we are implementing logical gates. And again, we can multiply stabilizers to our logical gates, which will result in equivalent logical gates. And here we see, for example, equivalent logical XL chains. So on the left, basically any boundary connecting top to bottom represents a logical X. The logical Zs are then the Z chains that connect the left border to the right border. And we can check that, for example, there is no X chain that connects the left and the right border. There would always be a parity check that fails. So we have at least two distinct logical gates: the Pauli X, top to bottom, and the Pauli Z, left to right. Any questions about that? Yeah. Yeah, it's in some sense, yes. Yeah, so the question was, is it due to the periodicity of the letters? And yes, that's the case. So originally, Kitaev considered a surface where the left and the right boundaries are actually connected, forming basically a pipe. And then the top and bottom boundaries are connected, forming a Möbius, or like, yeah, a donut, basically. But I didn't want to introduce this because this is even more abstract. But yeah, it's due to the periodicity. Any other questions? Okay. So now we really can think in terms of chains and loops. We don't need to think about Pauli operators anymore. We don't need to calculate if something commutes. We just think about chains propagating top to bottom, left to right. And if we think about why we do quantum error correction, so during the execution of any logical circuit, we want to avoid to accidentally flip our qubit or do logical Z or logical X. So what we actually want to avoid is that errors accumulate that will form a chain that connects boundaries. That's our only task. Avoid that the decoder or avoid that errors accumulate that connect borders. And now we can easily understand that if we increase the size of the surface code, then we need longer and longer chains to actually implement a logical gate. And it becomes more and more improbable that this will happen if the noise is very small. And that's basically where the threshold theorem argument comes from. If you have a huge patch of the surface code with, let's say, 2-3 million physical qubits, then it's very unlikely that in one round of syndrome measurements, we will suddenly have, I don't know, 5,000, 6,000 qubits flipped that form a chain connecting the boundaries. So that's the argument in the threshold theorem. All right. So how many errors can we correct in the surface code? We know that we have d squared data qubits arranged in a lattice, and we have d squared minus 1 ancilla qubits. And it can be shown, as mentioned in the notebook, that we can correct up to d minus 1/2 errors. And we can easily think about this like, let's say we have an error chain that is close to that starts at a boundary and is very close to the middle. As soon as it crosses the boundary, the middle of the code, we cannot anymore differentiate between a shorter chain that started on the other side of the surface code. So basically a decoder will most likely pick the shorter chain because it's more probable, and then we will close the chain. And that's where logical errors occur. So in the end, we can say that the surface code is a d squared 1D CSS code. So it encodes d squared physical qubits into one logical qubit. So a massive overhead, but it gives us very good protection. Any questions so far? Yeah, so the question was if the ancilla qubits are of course also noisy because they're physical qubits. Does that have any effect on the the number of errors we can detect or correct, and on the construction that we just presented? So of course, errors on the ancillas will affect the syndrome measurements. And there's a scheme where you just do repeated round of syndrome measurements to basically collect statistics about the correct syndrome measurement. And then you combine all this information to predict what was the true syndrome measurement. So let's say in the 5th round of syndrome measurement, one ancilla was flipped. So you measure the wrong syndrome. Then you continue your syndrome measurement rounds, and the ancilla is no longer flipped because we measured at the end of each syndrome measurement round. And this way we collect statistics about the true syndrome measurement, and we can use this to basically cope with errors in the ancillas. So there are a lot of tricks basically to make sure that we really avoid correcting, for example, faulty syndrome measurements. Okay. So now that we have a nice patch of the surface code and we know that we can detect and correct quite a lot of errors, let's think about how we can do actually quantum computation with the surface code. And again, we will go through all the logic gates and try to understand how quantum computation would look like. So since it's a CSS code, we can implement a C0 gate transversely by basically doing a C0 between two surface codes. But I think it becomes quickly clear that this is not ideal for superconducting qubits because usually we have connectivity constraints. This is only works well for neutral atoms or ion traps, where you can basically move the two patches physically in space together, apply some lasers to do the CNOT, and then move them away. That's how it's done in Quantinuum and, for example, QERA devices. And there are some nice videos on YouTube where you can really see how the logical qubits perform this dance where they are moved together. We apply a logical gate, they're moved apart and then measured separately. For superconducting qubits, we unfortunately need to do a little bit more complicated dance. So the idea is that there's a concept called lattice surgery, and that allows you to implement logical qubits or entangling gates by only doing operations at the boundary of the surface code. And that is, of course, easier for superconducting qubits because boundaries, they just mean a line of qubits that connects two patches of surface code. And that can be done on a superconducting device. And the idea here is, I will only sketch this. So what we have here is two patches. At the bottom of this H, we have two patches of surface code. Doesn't matter which distance. And the y-axis is time. And at each time step, we basically perform a syndrome measurement, acquiring data about the errors, and we will correct them. And then at some point, to apply a CNOT gate, we will introduce an ancilla logical surface code qubit. We will measure at the boundaries of the target and control with the ancilla. We will then perform another bunch of detection rounds and then do a destructive measurement of the ancilla qubit. And it can be shown that this basically performs a CNOT by just doing measurements at the boundaries of the surface code. And that's basically a scheme that allows us to do fault-tolerant quantum computing also on superconducting devices. Again, we have the problem of the non-Clifford gate. So we really need this T gate. And I mentioned at the beginning this scheme where you teleport, basically. You prepare an ancilla qubit in a specific state called a magic state. And then you use this teleportation circuit to apply a logical T gate on the psi. And the open question is, how do we do this T gate? Because Delphine already mentioned that we cannot do a logical T gate transversely. So we cannot just apply T gates on the physical qubits of our surface code. So what I will present today is one protocol. There are many. And that's a protocol for faulty state injection. So the idea is we start. So the psi-L is our logical qubit on which we want to apply a TL gate. And now we are only talking about the ancilla qubit, the 0. So what we do is we start with a single physical qubit, and we prepare it in the magic state TL plus, shown here. And then what we do is we basically grow the state. So we start performing stabilizer measurements around this physical qubit and quickly grow this physical qubit to a logical qubit. That's a scheme that works. So this is displayed here. So on the top left is basically our magic state qubit. That's just one physical qubit. And then we basically add more physical qubits, entangling them with the magic state, creating this surface code patch. And then we quickly grow it to a larger code distance to basically protect from errors. And it can be shown that this then represents the magic state that we need. Now, one problem is, since we start with a very low distance surface code, errors can be injected during that time. So our goal is to really make it as quickly as possible a large surface code. But at the beginning, we will definitely have errors, and it might be that we are not preparing actually the state that we prepared in the physical qubit. So it's a faulty operation, which might fail with some probability p. And in order to basically filter out magic states that were not prepared in the correct state, we use a protocol called magic state distillation. And that's basically this inception moment that I mentioned when Zohair asked about concatenated codes. So what we can do is we can basically prepare, let's say, 100 magic states Some of them might be faulty. And what we can then do is basically encode them in a quantum error correcting code where we can do the T-gate transversely. So as a reminder, the T-gate cannot be done transversely on CSS codes, but there exist other codes that allow for transversal implementation of the T-gate. And one example of such codes is the Muller-Reed 1513 code. That means 15 physical qubits are encoded into one logical qubit. And in this case, what we do is we use 15 surface codes, surface code patches, prepared either in 0 or in plus. Then we encode our surface code logical qubits in this Muller-Reed code, apply transversely the T-gate using our faulty T-states and the teleportation circuit shown up here. And then we measure basically for errors. And if we detect any error, we discard all our qubits and we repeat the process. But if we don't detect any errors, then it can be shown that the probability that we actually prepared this magic state is in leading order 35 times p to the p to 3. And that means that we actually reduced the error effectively, and that we can, if we repeat this magic state distillation protocol several times, create T-states with extremely high fidelity, but at a cost of a massive overhead. Because we really at each time need 15 surface code patches and need to basically measure if any error happened.
So if I remember correctly from the Eastern nil theorem,
yeah,
we cannot have any surface code which has where all gates can be applied transversely.
Yep.
So are we able to do the other Clifford gates here, or which gate can we not do transversely on the Muller-Reed code?
Yeah, so the Muller-Reed code allows to do the T-gate transversely, so it must have some other limitations. I have no idea which that is. I have to check the paper again, but we also don't care. We only want to use the transversal T-gate and then use the capability of the Muller-Reed code to detect errors. And that's all we care about. We're not continuing the computation with the Muller-Reed code. So we basically encode, then we apply transversely, we decode, we check for errors, and if we don't detect any errors, we have one magic state that we can use to apply T-gates to our surface code patches.
Okay, I see. Thanks.
Yeah. Okay, so now we can apply all gates that we need. We have a universal gate set for a logical qubit. And now I just want to sketch how fault-tolerant quantum computing will look like in 2100 when we have 10 billion physical qubits, and I don't know, this was the 100th edition of this conference, something like that. So the idea is that, so this is a proposal, TQuEst by 1QBit, a company that focuses on quantum resource estimation. And they basically proposed this core processor architecture for FTQC. At the top, we see the memory fabric. That's where the actual quantum computation takes place. So here all qubits are surface code qubits, and we do quantum computing via lattice surgery. And we basically see our data qubits in violet, and then the bus qubits in green. The bus qubits are just used to move around our data qubits in space, time, basically. And then at the bottom, we have our so-called multi-level magic state distillation factories. And those factories, their only job is to basically crunch out those magic states using this protocol that we just introduced, like growing those faulty magic states, distill them so that they have higher fidelity, and then repeat this process until we have very high fidelity magic states. And those are then stored in basically this buffer. And this will allow us to basically consume the magic states whenever we need to apply a T-gate. And if you think about the whole architecture, so each patch can correspond to d squared data qubits. So we need a lot of qubits, and it takes time to move them around, because moving means we stop measuring stabilizers on one side of the boundary and start measuring on the other side of the boundary. It moves the surface code by one step, basically. Delphine. Could you repeat that? So the question was if the computation will be really slow. And that's a great question. Let's have a look. So here, so here we have an example of how many T-gates are needed for fault-tolerant application or algorithm. So the background is this is a study by PsiQuantum. They concentrate on photonic quantum computing using fusion-based quantum computing. But it doesn't really matter. Same principle applies to superconducting qubits. And they basically analyzed how many T-gates we would need to, for example, break RSA with 4096 bits for the key. And what we can see is we need a huge number of logical qubits, and we need to execute a lot of T-gates in those algorithms. And remember, for each T-gate, we need to go through this whole distillation process. So now we could ask the question, what is the footprint of magic state distillation compared to actual computation? And that's basically what is shown here. So the red regions show that we are mostly doing actual computation. We're executing the algorithm, and magic state distillation is not a huge overhead. And then on the left side, we have basically applications where magic state distillation makes up a huge part of basically our computation. And now to Delphine's question. We have here 4 example applications. So I guess factoring means that we, for example, try to factor the keys of RSA. And you can see down here the runtime in seconds. And yeah, factoring can take up to 1 year. So this is basically why it's really important to understand at what speed we can execute operations on a quantum computer. So you can see that there's a huge difference if we can execute gates at a microsecond level or on a nanosecond level. This can be the difference between a decade and a month. So superconducting qubits are very well known for having fast gates. But for example, they need to move their logical qubits a lot because we cannot do transversal CNOTs. And then ion traps are known to be a bit slower, but they have some advantages when it comes to basically applying those transversal gates. But I think the core message is here that we really need to study what kind of distillation protocols we use, what kind of fault-tolerant gates we need, how large our surface code patches are, and then really understand what this means for future fault-tolerant architectures. So the one that I showed here is, of course, only an example. There might be more efficient ones. And that's basically the field of quantum resource estimation. And, for example, Microsoft has been leading in this domain. Any questions? Okay, everyone is shocked by the runtimes. So I'll skip the part about the decoder. I hope you can check that on your own when you have time. So what I didn't talk about today was how to basically use the syndrome measurement information to estimate where an error happened and how to avoid that long chains creep up in our surface code patches. And instead, I want to basically show you state-of-the-art experiments today. So remember, we want very large surface codes in the future with millions of physical qubits. But the question is, like, what can we do today? And I will talk about an experiment by Google done this year, which for the first time showed that the threshold theorem actually works and that we can observe it on real hardware. So we can see exponential suppression, which was an amazing result because it confirmed theory. And yeah, I will just quickly go through the main points of this experiment. So the idea is that we want to do a quantum memory experiment. So we will prepare surface code in a known logical state, and we just want to preserve it for as many rounds of quantum error detection as possible. And the setup is that Google is developing superconducting quantum devices. The device is called Sycamore, and for this experiment, they used a device with 105 qubits based on the Transmon architecture with tunable couplers. They implemented code distances for the surface code 3, 5, and 7. And just to have an idea of the gate speed, so for single qubit rotations, we are talking about 25 nanoseconds. And for entangling gates, or the CZ gate, we're talking about 42 nanoseconds. Reducing the gate speed is not always ideal because it can cause effects like leakage, where we basically leak out the computational space, and then our computation is not well defined. Since those experiments can take a very long time, they also implemented calibration strategies such as TLS mitigation. So TLS are level systems that basically couple to neighboring qubits, and they reduce the fidelity of the qubit drastically for a short period of time. That could be minutes to hours. And they're transient, so you basically, when you measure the T1 time of a qubit for a long time, you might see a massive drop in T1 time, and at some time it will recover again. And if your experiments take a long time, you need to take into account such effects. And the main result is that they demonstrated that the lifetime of the logical qubit is 2 times the lifetime of their best physical qubit on the chip, and that they can do real-time decoding. So basically they can process incoming syndrome information as quickly as it takes to generate them, which is really important.
Quick question from
yeah.
our online participants. Are your slides uploaded now on the...
No, we will upload them later today, and they
Right.
contain also much more information. So,
Excellent. So they will be uploaded later today.
Yep. Okay. So one thing that they had to basically consider during that experiment is the effect of leakage. So in quantum error correction, we usually assume independent, uncorrelated errors. And leakage is an effect where basically your qubit escapes out of the 0-1 subsystem, and that causes correlated errors. So one part of the engineering challenge was to basically reduce leakage or use mechanisms to basically transport leakage away from the data qubits. And the example here shown is assume that during one round of error correction, we have a leakage on one of the data qubits. Then through the measurement of the ancillars, the leakage is spread on the surface code patch. And it takes a few rounds of quantum error correction before the leakage is gone due to the T2 and T1 time of the second or higher energy level states. And they developed a technique called data qubit leakage removal, where they use a so-called leakage ISWAP gate to transfer high energy states to the ancillar qubits, and then to basically wait for them to dissipate and then measure them to reset them. So you can see that even, or at least on the hardware level, there are so many mitigation strategies that you need to consider and so many effects before you can actually start implementing those very large surface codes. So the main results are shown here. So the x-axis is quantum error correction cycles. So in each cycle, we obtain a set of syndromes by measuring basically all the ancillars. And the y-axis is the logical error rate. And of course, since currently we don't have perfect physical qubits, if you increase the number of cycles, the logical error rate will slowly increase. But for larger surface code distances, the logical error rate should increase more slower than for smaller surface codes. And that's what's shown here. For example, for D7, we see a drastic reduced logical error rate compared to, for example, code distance 5. And we also see, so they plotted here the best physical qubit. So we can see that the error rate of the physical qubit or distance for a single physical qubit is much higher than the one of distance 5 and distance 7. And that's the first result that we can implement surface codes below this threshold that was basically promised by this threshold theorem that we mentioned at the beginning. So so Google proved that they are operating their devices below threshold, and that we can actually achieve exponential suppression of errors. Yeah, so quantum error correction is a really fascinating field. I think we have seen today that we have many different types of research going on. So we have mathematicians who work on designing new codes with various properties. We have the hardware engineers who really need to think about how to remove leakage, how to make our gates faster, how to calibrate the device and maintain calibration over several hours. And there are many, many more topics that we didn't cover today, like different families of codes, such as quantum LDPC codes or color codes. There are codes such as bosonic codes that rely on different types of qubits, not just a two-level system. And we have seen that quantum resource estimation can yield interesting results when it comes to runtime of fault-tolerant quantum computation. So yeah, a really interesting field, and we are slowly moving from like theory to practical implementation of the papers that were published in the 70s, 80s, and 90s. So it's really exciting to basically see all those real-world demonstration of the results that theory predicted 20, 30 years ago. All right. So I will upload the slides later. Please have a look. We didn't talk about decoders, for example, today. And there's also a second notebook on estimating the surface code threshold. So if you're interested in how that works, please have a look. Thanks.
Thank you very much. Let's see what questions we have.
Okay. So Jerome, you mentioned that we are already outperforming just like the best physical qubit. How much does it depend on the quality of qubits? Like, does it depend more on the median, or is it extremely affected by one single very bad qubit?
That's a good question. So if you have a single very bad qubit, you would most likely get a flipped ancilla measurement every round. And this would effectively reduce your code size. So if you have too many of them, you're basically just operating a lower distance surface code. So you're really talking about average qubit fidelity, and all your qubits should be at least on average good. Okay, so a single bad qubit can effectively reduce your surface code size.
Okay, so effectively we want like the minimum threshold of all the qubits is what defines how good our qubit is. So even if the best qubit was like significantly worse, but still better than the worst qubit, it shouldn't affect anything.
Okay, can you repeat that?
So instead of like this whole spread of qubits, if all of the qubits were the same as the absolute worst qubit, there shouldn't be any difference?
If they were, yeah, that's a good question. So the threshold theorem just abstracts away the error by saying physical error rate P, and we have seen there are many error mechanisms. So I'm not 100% sure how to reply here. You would basically really simulate and see what happens. But of course, if all your qubits are bad, then you're basically just shifting to a higher logical error rate. As I guess it's sketched here. So basically, you would move to the right side by just having all your qubits being worse. But it's a good question. So what happens if you have like parts of your surface code, like a region where you have bad qubits? What happens? And I would expect that most likely you would operate in a regime to the right then. Yeah.
Thanks.
Interesting. More questions, please.
To help the code, is it possible to use two types of, say, qubits, superconducting and transmon, or I mean the transmon and ion trap hybridizing?
I could imagine that you can build schemes.
So
I'm
you
a
can
bit,
combine the advantages of two.
yeah, but then the question is, how do you coherently swap quantum information between the two
Yeah, that's the
modalities?
point.
And most likely you would, like, this can be done, but you most likely then need to be careful that you do this fault tolerantly. And yeah, I wouldn't know how such an analysis would look like. Zoe has a comment on that.
Actually, you can switch between different types of atoms. So, for example, at least as far as I'm aware, in ion traps, for example, you can use rubidium, which you can do gates very easily with that. But there's the theory that you could have potassium atoms as well, which you can just use for storing, or which has a longer lifetime, but it's harder to do gates. And you could effectively swap between them as you need them. So I guess at least that is one thing being considered.
Okay. Good. One more from the room.
Yeah, just like, well, thank you for the presentation, it was really good. And yeah, the quantum resources, like plots that you've shown, they're like are based on the idea that like in the future we're gonna use the surface code, right?
That's correct, yeah.
So what, like, there are other codes that maybe like scale better as like in terms of distance, and like what will change from that point of view for the quantum resources?
So for example, there's the family of quantum LDPC codes. So the name is low density parity check, and the name already suggests that your stabilizers have a lower weight. But it comes at a drawback that you, for example, need long-range interactions on your chip, which is not difficult, not easy to implement on a superconducting quantum architecture. But yeah, there are definitely codes that reduce the number of physical qubits needed, and that's of course studied and also included in those quantum resource estimates. Yeah, but people, like, the field started from let's have a surface code, let's assume a fixed physical error rate, and we want a fixed target logical error rate. What do we get? And from that's basically an upper bound. And now people are working on selecting better quantum error codes, and they're basically those Python libraries that allow you now to define, okay, I want this code, this logical error rate, what do I get for Shaw's algorithm, for example?
Thank you.
Thanks for great presentations. So if one is coding in Qiskit, for example, and running stuff on the real IBM hardware, is there anything, any of these algorithms that are running behind the scenes, so to speak, or do you have to implement everything explicitly yourself?
Good question. So regarding the codes themselves, so they have a fixed, basically, the quantum error correction cycle, so the way you measure the syndromes are fixed. So that's usually a few lines of codes, but of course there are libraries that basically allow you to load the circuits directly into your algorithm. But then on the lower level, we're talking about error suppression, error mitigation. So the topic that Zohaya covered yesterday, there, for example, IBM automatically injects optimizations to basically reduce the error rate of your entangling gates, of your single qubit rotations. I don't know what IBM is doing behind the scenes. I know that they work with Q-control, algorithmic, to basically implement suppression and mitigation. We at VTT, currently, when we're working with our superconducting devices, we really, most of the time, manually write down our quantum circuits and really carefully analyze what are the effects where the noise source is. So we are not at the stage where you can just basically import surface code and just run it. So, but I assume if the fidelities improve over time, we will reach the stage where this just becomes an abstraction layer in the quantum operating system.
Okay, thank you. One more question.
I have one more. You mentioned the VTT systems. Is there plans to use surface codes on the newer one coming around?
Yeah, so VTT is currently developing or co-developing with IQM a superconducting device with a lattice topology with 54 superconducting qubits. And it's of course natural then to basically implement the surface code and see what's currently possible. We're still in the process of benchmarking the device and learning more about the device, so it's not clear at this point how successful it will be. But it's definitely a very interesting topic, and personally, I'm also interested in the state injection procedure here. Yesterday, I found a paper that implemented this protocol on the IBM FEST device, so the latest IBM device with 156 superconducting qubit in a heavy hex topology. It would be very interesting to see if we can do something similar on our devices, so growing a surface code from a single qubit to, let's say, distance 3, and just measure the preparation error.
Let's dive into this afternoon. We start with an hour of hardware, overview of the hardware, and then we dive into quantum finance use cases, quantum Monte Carlo and quantum finance. And a reminder to keep the questions coming in for the online participants. Write your questions in HackMD or just the Zoom chat, that works too. And let's begin. Yes, you do.
Hi, hello. I'm very happy to be with you today and present about the hardware behind what we perceive as quantum computation. I'm Eleftherios and I come from Chalmers X Labs. I'm an engineer there at Chalmers in Gothenburg. So I think this is a familiar picture. Forgive my terrible Photoshop, but we can imagine that we have a Qiskit circuit ready to be compiled on our screens. Let's pause for a moment to think after we after we press enter, or after we ask the circuit to compile. Let's imagine that in order for this to be realized, multiple cutting-edge technologies of many different disciplines in physics and engineering must be coordinated. We're talking about cryogenic engineering, micro and nano fabrication techniques, microwave engineering, microwave pulse creation, techniques to manipulate quantum states. I can think of material science, superconducting physics, signal processing, probably a lot more. And all of them has to be at the extreme cutting edge. So my motivation is, I would like to give you a taste of what is happening here in a quantum computation lab. We want to build a quantum computer, right? So we need to think what is a zero, what is one. Of course, there are many physical models that propose to implement the quantum zero and quantum one. For example, cold atoms, ion traps, photons, and so on. In Chalmers, we focus on superconducting qubits, transverse in particular. And the very big advantage is that these kind of circuits are kind of big, are almost macroscopic. So this allows us to exploit the vast experience from fabrication techniques. These quantum devices can be lithographically designed. Can be designed in the computer, and using lithography techniques, they can be manufactured in a clean room. Before we talk about what is a transmon, let's talk about what is not a transmon, or actually what is almost a transmon. If we see this is a typical quantum harmonic oscillator, a simple LC circuit that can be very easily fabricated in the clean room. The property that a qubit must fulfill is that we must be able to select with very high precision our 0 and 1. And we do this by relying on frequency selectivity. Unfortunately, a quantum harmonic oscillator does not fulfill this condition. Because the energy levels are at equal distance, you cannot distinguish what is 0, what is 1 when you set a microwave pulse. All of them are the same. So what we do is do a slight modification on the Hamiltonian. You see here is a typical harmonic oscillator Hamiltonian. But if instead introduce a nonlinear inductor instead of a classical inductor, this can be embedded by what we call a Josephson junction. The Hamiltonian changes a little bit. Instead of a square, it becomes a cosine. And if we expand the cosine, it so slightly changes the shape of the well. And this makes the lower energy level to be a little bit different in frequency. This slight anharmonicity is what exactly allows us to precisely select what is 0 and what is 1 by targeting only the desired frequency for our state. This Josephson junction in practice is a sandwich. We have two layers of pure aluminum, superconducting aluminum, and we let to slip in an insulator, an oxidized aluminum, to act as a barrier that the electrons that form Cooper pairs have to tunnel through. This is how the Josephson junction is implemented, and this is what in practice gives a cosine term in the Hamiltonian that so slightly modifies, makes the potential well so slightly non-harmonic. Okay, the requirement is to precisely select the 0 and 1. Having the anharmonicity, unfortunately, is not enough. Let's try to do some back-of-the-envelope calculation of why this is not enough. I will tell you that in the majority of labs that work with superconducting qubits, the frequencies range about 3, 4, 5 gigahertz. Let's start with this, and it will become clear later. What does 5 gigahertz mean? If we remember from our early physics, it means about, using the Planck constant, this number, roughly 4, 10 to the negative 4 joule. In order to select the 0 and 1, of course, there must be no doubt that we distinguish it from thermal noise. Otherwise, it's useless. Let's make a back-of-the-envelope requirement that we want it to be 1 order of magnitude clearer than the background noise. If you come to the Boltzmann constant, this requires a frequency down to the few millikelvin. In practice, it's more closely to 10 millikelvin. So this is the requirement in order to implement qubits on superconducting devices. Temperatures extremely low, just some millikelvin above the absolute zero. And that's why fridges like this are dominating in modern quantum technology labs that provide as much shielding as possible from environment heat, environment radiation, and provide a vacuum as much tight as possible, so deep inside we can house and protect the qubit devices. Okay, so how do we get there? How do we get to temperature just a fraction, just a hair above the absolute zero? Let me give you a brief description of how does a modern cryostat work. The cooling consists of two stages. The first employs what is known as a pulse tube. The basic idea is 200 years old. It's just a steering engine. Of course, in modern times, it is engineered to the extreme. Let's see how it works. This is how a typical pulse tube cryocooler looks like. We identify the key components, a compressor, and some heat sinks. The hot heat exchangers are there to dispose of unwanted heat. The cold heat exchanger, you can imagine that this is the most important part. This is where the fridge is connected. So let's try to imagine how this operates. We have a compressor. So first of all, it will compress, right? Compressor means that under constant volume, the temperature will be increased. We don't want that. We want to get rid of this excessive heat. So the heat exchangers, and most importantly, this mesh that you see here, this is called the regenerator, and it's there to protect the cold end from this undesired heat. Think of this as a very, like a metal sponge that has a very, very big surface area that very quickly dissipate heat and protect the cold end. Also this here, it's just, here in the tube we have a helium-4, almost ideal gas. This green box that you see here is just, again, the same gas, it's nothing different. This is called the displacer gas, and this is engineered to always stay within the pulse tube. As the pressure wave moves, again, the displacer gas will reach this needle valve. And because of high pressure, first heat will continue to be dissipated. But because of the pressure, the needle valve will let excessive gas to travel through this tube and this buffer tank. These are the important things that allow the cooling. What they do is create a lag between the pressure wave and the position of the compressor. This becomes clear in the next step. Now the displacer gas here has been all the way to the right, but the compressor is about to start moving to the left. So displacer gas moves to the right, still moves to the right, but the compressor is about to move to the left. But moving to the left requires the gas near the cold end to do work. What is the only way that this gas can do work? By absorbing heat. So it absorbs heat, because this is the only way to produce work, by whatever is attached to the cold end. And this is how cooling is achieved. After the compressor has returned to the original position, the gas has returned to almost the room temperature. Everything else the same, except that at the cold end, ever so slightly, the temperature has decreased, just a little bit. This back and forth has frequency about 1 Hertz. So if you go to a lab that operates cryo-cool like that, you hear this characteristic chup, 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 chup at frequency 1 Hertz. It's the compressor of the pulse tube doing its work. And after after about 24 hours, this little by little has reduced the temperature to about 4 Kelvin. So this is about the temperature that the many components of the cooling can kick in. At 4 Kelvin, the helium-4 can start to liquefying. What is the second stage? What is the heart of the cooling? What does allow us to reach these extremely low millikelvin temperatures? Let's take a look at the phase diagram of the mixer between helium-3 and helium-4. It's not only helium-4. We let circulate a little bit of helium-3. Although it's very expensive, it's absolutely necessary for the cooling to be achieved. If we observe the phase diagram of the mixer, we see that below about 0.87 Kelvin, the mixer separates. So helium-3 and helium-4 can no longer be mixed. Think about olive oil and water. They cannot be mixed. The concentrate phase of helium-3 floats, because helium-3 is a lot lighter, above the helium-4. And there is one very specific region of this phase diagram that allows the cooling. Here it is. You see the x-axis shows the concentration of helium-3 in the mixer. You see, okay, I told you that these liquids, these mixtures cannot be mixed. This is not always true. You see, at very small concentrations, even at completely absolute zero, a little but still significant part of helium-3 can still be dissolved in helium-4. This number is about 6.6. This is what allows everything. Let's try to, let's take a little bit deeper look. These are the insides of the lower stage of a modern dilution refrigerator. What I have talked about is happening here. You see a very small cylinder. This is called the mixing chamber, and this is where the 10 millikelvin are reached. This metal plate houses our experiment, our quantum computer. Here, the mixing chamber is where we have the two liquids separated. So, what allows the cooling is the fact that the two phases where the helium-3 is concentrated and the helium-3 is dilute among helium-4 have different enthalpies. This means that the helium-3, when it makes a choice to evaporate in the dilute phase, and I'm using the word evaporation on purpose. You know, when you have sweat on your hand and it blows, the evaporation makes you feel cooler. Still, before the dilution refrigerators, there were refrigerators that were using typical helium-3 or helium-4 evaporation, but with poor efficiency. This is still some kind of evaporation. It's just that the helium-3 evaporates from a very dense phase to a more dilute. And this comes with heat absorption because the helium-3 feels more welcome among the more inert helium-4. And whatever little bit of helium-3 is there, feels some kind of binding among each other. This increasing binding energy is produced by the heat absorption. So a little by little, as helium-3 makes the decision to jump, to evaporate through the dilute phase, heat is absorbed from the environment. Okay, but if helium-3 continues to stay there, you cannot have a circle, and at some point the cooling will stop. So we need to make a loop. We need to have this process continuously occurring.
Excuse me, Eleftherios, there's a question here from an online participant. Is there any consumption of helium? If so, what is the helium consumption rate? And what is the helium-3 over helium-4 ratio?
So in a typical mixer, I don't know the exact volumes, but it's 6.6 helium-3 parts for 100 parts of helium-4. So it's 6.6% helium-3 in the mixer.
And I guess by consumption, it means whether you need to refill it, sort of?
Helium-3 is so expensive that every slight leakage makes us panic. So hopefully no refilling happens. There are a lot of measures that make sure that no leakage is happening. It's really a reason to panic if helium-3 is missing.
My own bonus question then, how expensive?
I don't know the values. You know, helium-3 is a byproduct, I don't know the money, but helium-3 is a byproduct of nuclear plant operations, so it's very, very difficult to produce. I don't know the exact, but it's super expensive. So we need to continue the circle.
Sorry, just like one quick question. So if I remember correctly, helium-4, at least that's a Bose-Einstein condensate, so it will always leak out or it will like leach into it. So is there any specific way you try to prevent that, or are you only focused on preventing like helium-3 leakages?
There are a lot of valves that are in place, and a lot of safety checks that make sure that valves are always shut. From time to time, we perform leak checks, make sure that nothing is leaking.
Thank you.
Yeah. There's always a danger, but yeah. So we need to keep the circle going. The mixing chamber is at 10 millikelvin. Above, we have another chamber. Let me show you here. This is called the still. It comes from the word distillation. The still chamber lies at about 800 millikelvin. This temperature difference creates a pressure gradient that is enough to suck the helium-3. Helium-3 is lighter, so it's more mobile. So continuously because of the temperature difference, helium-3 is sucked up in the distillation chamber. There, because again helium-3 is more mobile, it has a lower zero-point energy, it's easier to evaporate. It has significantly higher vapor pressure, to use the correct terminology. So if we put a pump here, the helium-3 very efficiently will be pumped away. So here you don't see it, but there are a system of pumps that make sure that the circle is closed. So after some travel through the pumps, again, the helium-3 will come back again through a compressor, and the circle will continue internal forever or until we interrupt it. So this is how we reach millikelvin temperature, by evaporating a little bit of helium-3 in a dilute helium-4 mixture. And there, now that we have our very low temperature, we put finally our quantum devices. Before I actually talk about the quantum devices, let me give you a slide of how is this fabricated. It's not my expertise, but I think I find it at least very interesting. So let me try to give you a taste. We begin with a silicon layer, a wafer of silicon. The ground plate of a chip, in our case, is aluminum. They can be tantalum or other metals. In Chalmers, we use aluminum for the ground plane. We will let it evaporate for quite some time, and about a layer, a few hundred nanometers, is created. Then we apply it with a polymer. We spin a thin layer of polymer. This polymer has the property that is reactive to light. If optical light hits it, the chemical composition changes. So let's do that. Let's shine light on it. In our computer, we have designed a pattern that the optical lasers pattern on the photoresist. This wiggly line is called a resonator. It plays an important role in the quantum processor. Next, after we dissolve the features that we want to etch, we apply an acid that eats away the metal, etches away the aluminum. So it leaves a canyon right in the middle with the features that we want to expose. And finally, we dissolve this polymer mask, and here in the middle, the canyon of aluminum appears. This is electrically separated from the rest of the ground plane, so there is a potential difference. And this is, in the end, an element of the quantum processor. This is what that is called the resonator. Okay, these are the basic steps. In order to do qubits, because qubits required more finer features, about a few hundred nanometers, optical techniques are not precise enough. So we use EBM, electron beam lithography, in order to etch the pattern of the qubit, the Josephson junctions. But the idea is the same.
Sorry, quick question again here from the chat. So what does cold heat mean? Cold heat.
What is that?
Seems like a contradiction, but I'm sure it means something very cool. Cold heat exchanger. Hot heat exchanger.
So they are both heat exchangers that one operates at cold temperatures and the other are hot. Cold. Okay, so at this exchanger we connect what we want to cool down. So imagine that the fridge is connected here. Okay, so I should have put a comma there. So it's a heat exchanger that operates at, that's supposed to be cold, to cool down whatever you connect there. Okay, so we spent many hours at the clean room, and in the end we get something like this. These are the pictures that my colleague Anuja Agriwal from Charmel has so kindly shared with me. So this is what it looks like. This is a small quantum processor with only 5 qubits. Let's take a look at the anatomy of such a quantum device. As you scale up, the features are very similar, so I think we would get a good idea. First, the basic elements. These wiggly lines, we have 5 here, are called resonators. They allow us to do measurements. What uses to do operations on the qubits if you can measure it, right? These are the qubits, the protagonist of the show, where we encode our quantum zeros and ones. And these are the couplers. Okay, I have no idea why they do like, because Anush has an experimental 2-qubit gate here, but okay. These are what allows the other important element of quantum computation, quantum entangling. Because in order to do algorithms, you need 2-qubit entanglement somehow. Okay, so these are the elements. But what use they are if you cannot interact with them? So we see more features. We see these lines. They are called qubit. Yes.
One question about the look of the qubits or the shape of the qubits.
Yeah.
Could you?
So you typically are familiar with the cross.
Mm-hmm.
Yeah. I'm not a designer, so I don't really know what happens inside. But in the end, they implement a capacitor and an inductor. So yeah, it's hard to convince you. I'm not even convinced, but this design. This design is this is an island of aluminum that separates the rest of the aluminum, the ground plane. And this creates a capacitance, and here there is an inductor, but because it's at nanometer scale, you cannot really tell.
Okay, and the Josephson junction is basically in the middle where we have the line, or where would it? I guess we cannot see it really, but
you cannot see because this is an optical photography, and Josephson junctions are nanometers wide.
So it's in the middle.
Yeah.
All right. Thanks.
In order to make use of these elements, we need to interact somehow with them. So we see a lot of lines here. We see XY line. We see qubit control lines, which they are called XY lines. We're going to see why. We also see a line, very special line, that has entrance and exit. This have only entrance. This has entrance and exit. So that's why it's called a feed-through line. And this is how we read, how we do readout. And also we see lines connected to the coupler. Here we introduce both AC signals and DC signals and DC current. This is how we implement 2-qubit gates. Because a coupler, at least in our architecture, a coupler consists of a squid, a loop. So if you have a superconducting loop, you need to thread current through the loop. Okay, so this is how a quantum chip looks. These were the fundamental elements of quantum chip. How do we use it? How we do measurement and how we do control. The answer is with microwave pulses that either only send to do control or send and receive back to do measurement. In our lab, it would look something like that. So let's play it once again. So you see microwave pulse coming off an RF generator, travel through the device, and in the end the readout pulse will return back and will be analyzed to tell us its adventures through the chip. Let's take a little closer look to what is quantum measurement and quantum control. In the end of the day, I cannot convince you, but in the end of the day, there is a qubit and also capacitively connected to a drive line. So this inner red circle and this electrical circuit tell the same story. It's an almost LC circuit, a capacitor, and an alternating voltage. And we can write equations of motions for this, right? We can write Kirchhoff rules. I was advised not to show the Lagrangian because, does it mean anything to you? It barely means nothing to me right now. But I wanted to make the point that we have the equations of motion. So we can find the Lagrangian. So if we have the Lagrangian, we can find the Hamiltonian. And this is the argument I want to make. Somehow it's tedious, but it's a straightforward work to find the Hamiltonian that allows us to do control. And in the end, if we decide to go to the rotating frame, the frame that the qubit leaves, we will see that the Hamiltonian can be expressed in terms of the X-white Pauli matrices. And you know that these are the generators of rotations in the SU2 space, right? So every control operations, remember the X-Y lines? Every control operation can be represented by a rotation in a sphere that is called the block sphere, something like that. This tries to represent a rotation from the 0 to 1. So this could be an X gate in our representation. The envelope E is something like the envelope E, the quadrature I, and the quadrature Q is something that the RF generator controls. This is something we can program. These are voltage amplitudes and voltage and shapes of pulses. So this is something that we can control and program precisely. Okay, so this is the main, the idea of how we can start doing control. But what about measurement? You know, in the quantum world, measurement has a very, very different meaning than we understand in the classical world. And the qubit is something so fragile and so sensitive that we need to do the best we can to protect it. So these are kind of contradictory ideas. You want to measure it, but this is a violent operation, right? You are in danger of destructing the state of the qubit. Let's see how we do it. Again, in the end of the day, we use a resonator, capacitively connected to a qubit. What we saw earlier in the actual photograph of the device. And in the end of the day, we have electrical circuits that again we can find Kirchhoff rules, Lagrangian, and in the end we can find the Hamiltonian. I hope I convince you that I'm telling the truth, that this is the James Cummings Hamiltonian that describes the interaction between qubit and resonator. This looks like the number of operator of a resonator, a quantum harmonic oscillator. This looks like the Hamiltonian of a two-level system of the qubit. And here we see the mixing of a creation and annihilation operators, or the qubit levels, the sigma plus and minus, and the harmonic oscillator, the resonator levels. So I think I can convince you that this means exchange of energy between the resonator and the qubit. And G is the coupling factor. It depends on how the designer have designed the capacitor here. What is the distance? What is the area of the plates. The important parameter here is the detuning. We want the frequency of the resonator to be very far apart of the qubit, because we want the qubit to be protected. In the dispersive limit, if we expand this Hamiltonian, we have the dispersive James Hamiltonian. Where should we look? This is the resonator. Whenever we do a measurement, in the end of the day, we take eigenvalues of this operator. And in the end, the eigenvalue will depend on what is in this parenthesis. Let's take a look at this parenthesis. We see SZ, but SZ is the operator of the qubit. This means that by this design, whatever we measure on the resonator explicitly depends on the state of the qubit. So we can infer the state of the qubit without measuring directly the qubit, because the state of the resonator depends on the state of the qubit. Let me repeat that. Here on the right, we send a resonator, and the resonator is absorbed.
In the previous slide, the qubit and resonator should be the same type?
The same?
Resonator and qubit.
Yes.
Both of them, they should be the same type. Or they can be.
The resonator is a classical resonator,
Okay.
classical harmonic oscillator.
That's just, and the alpha.
Yeah, okay, yeah, okay. Oh, you're absolutely right. So yeah, I use the letter J to say that this Joseph von Junction, it's a bad design. And it should be clarified here.
And the alpha there is just the quadrature, right? Is a position and momentum.
Yeah, it's the creation of operator of the quantum harmonic oscillator.
So how it's related to A then? The resonate.
So you mean
Sigma
here?
is the qubit, alpha is the resonate, right?
Yeah, my bad. This and this are the same symbol.
I see.
Yeah, yeah. I apologize.
I
for
thought
that.
that's the quadrature position.
No, both of them are creation operation. I apologize for that. It's my omission. So let me insist on this dispersive James Hamiltonian. Here on the right, we send a pulse at a purple frequency, a blue frequency, and you see it is absorbed by this resonator, and it deposits some energy. So we see a dip. Now we send an excitation pulse, and the qubit is at a different state, is at the excited state. And now, in order to absorb the resonator, we need a different frequency. So by exciting or not the qubit, the resonator profile is completely different. This is what allows us to distinguish between the quantum zero without one, and importantly, without disturbing the qubit. This is a quantum non-demolition measurement. This is a dispersive quantum measurement. This is the bread and butter of transport measurements. All the nice measurements that we see, all the Rabi oscillations, the Ramsey oscillations, the T1 exponential decays, the randomized benchmarkings, the two-state discriminations. All of these nice pictures rely on this fact that the resonator has a different profile depending on what the qubit is doing, without the qubit being disturbed.
So maybe you already answered this, but there's a quick question here in the chat. Reading the state does not destroy it, or did I understand wrong?
No, the qubit remains in the specific state that it was before measurement. It's a quantum non-demolition measurement.
Quantum non-demolition measurement.
No, yes.
Cool. Mm-hmm. Maybe this is not on topic right now. You feel free to come back to this question, but there's another one here. What are the main challenges in fabricating quantum chips?
I'm not a fabrication guy, but at least in our group, we want to understand so the important thing is the fidelity of the operations. how can we protect the qubit from environmental decoherence, and how does fabrication can help with that. So what materials should be used? What are the techniques? It's a huge topic. But I would say how can we best protect the qubits from environmental noise. I briefly touched on the frequency of the resonator. So we talked about that the quantum processor consists of resonator, qubits, couplers. You see, in order to precisely perform operations on this processor, you need to have information, very precise information on a very big, extremely big number of parameters. I briefly touched on the resonator spectroscopy. Let's see it one more time. So we send a frequency, nothing happens. We send another frequency, nothing happens. We send another frequency, oh, it got absorbed. So that's why we saw a dip when we analyzed the resonator back. So this is how we do measurements. For example, in the resonator spectroscopy, we send many resonator frequencies, and we identify the characteristic dip. And by this, we expose one piece of information about the quantum processor. The dip shows us the frequency that we need to operate the resonator at. But this is, there are so many parameters. And soon, in order to operate a quantum processor, this becomes a really seriously challenge. What can you do? Manual calibration, okay, it can only get you so far. So what we do at Chalmers is describing the calibration procedure by a graph, where each node represents a very specific measurement. Resonator spectroscopy, qubit spectroscopy, Rabi oscillations. Each one of them reveals a piece of the puzzle. And in the end, little by little, measurement by measurement, you end up to have a complete picture of the state of the quantum processor that allows you to perform high fidelity operations. This on its own becomes a problem on its own. Programming, software engineering, many disciplines come to this because it's not just doing this. In order to do this efficiency, you need to take into account how you store data, how you manage data, how do you analyze data, how you efficiently interact with the peculiarities of your instruments, with the peculiarities of the devices. Very quickly, the requirements blow up. Here at Chalmers, we have developed our in-house automatic calibration suite, which is open source and available to anyone. And you can find it at this link. With this, my presentation is concluded. I would like to thank you for the invitation. Thank you very much.
Very good. Thank you very much. The mic is around.
Hi. Thanks for the presentation. I have one question about the calibration. So that's an auto calibration. Does your tool provide basically a dashboard to follow the calibration and see relevant plots?
Yes. We don't have a dashboard. We use an CLI, command line interface. But yeah, everything is there. The database, the plots, all the state of the parameters. Yeah.
And I see you do 3 states discrimination.
This is a yeah. Please go on.
Yeah, I'm just interested. Why do you need the third state? Does it help you to identify?
Yeah, in order to do 2-qubit gates, we do CZ gates. So the CZ gate exploits the second excited state of the transpond. So we need to move outside of the computational state. So if we can discriminate it also if we can discriminate also the third state, it helps us to calibrate this CZ gate.
Okay, thanks.
Thank you very much. Also, this is just an example. In reality, the graph is unfortunately a lot bigger.
Okay, one more question.
Thanks for the presentation. About the measuring and manipulating of the qubit, are they done in a different frequencies?
Yes. Where is delta? Yes. And it's very important that, so to give you an idea, omega q, the qubit is around 3 to 5 gigahertz. I would say 3 to 4 most typically. The resonator is between 6 and 7. So the 25 qubit device at Chalmers has this number of frequencies. And we want it to be very far separated to protect the qubit from the resonator signals. So yeah, they're 2 gigahertz apart at least.
Okay, the higher frequency of the measurement, that's the reason that it doesn't touch the qubit states, right?
Yeah.
Because it's high and then, okay.
First of all, it's very far separated. G is about 100 megahertz decoupling. So yeah, the decoupling is 2 gigahertz. And also we want the resonator to be higher than the qubit, because if it was lower than a qubit, say that the qubit is at 4, and let's say that qubit is at 2. You made a mistake, the fabricators made a mistake and put it there where the higher harmonics of the resonator hit the qubit. That would be very bad.
I see.
Because you cannot guarantee that fabrication will very precisely fabricate the frequency. So in order to avoid that the harmonics of the resonator hit the qubit, we put it at higher frequencies.
Okay, good, thanks.
Looks like a beamer, latex beamer slides. No?
Yes, I think that's the case.
Okay, welcome back. Now we switch gears from the nitty-gritty details of the hardware up to a higher abstraction level and what you can actually do in real-life cases with a quantum computer in the domain of quantum finance. I guess, option pricing. And so let the questions keep flowing. Don't hesitate to raise your hand if you have a question, and that includes people online as well. And yes, let's start. Over to Björn Lövdahl from SEB.
Thank you very much, Tor. Can you hear me all right online as well? I hope so. So I'm here as part of a collaboration to hopefully teach you one or two things about how we can apply quantum computers in the field of finance. So it's a collaboration between SEB, which I represent, and also Handelsbanken and RISE. And I will kick off by presenting option pricing on a quantum computer. So first, we must define what an option is and why do you want to price it. So a so-called European call or put option on a stock, it's something that gives you the right to buy or sell the stock S at a known price K at some predetermined time T. This price K, this is known as the strike price, and T is the time to expiry of the option. And these options are often sold by banks to their clients because a client wants some certain type of payoff. And that's just the case. At expiry, the client will receive this payoff, which is some function phi of ST, which is the price at expiry. And in the case of a European call option, it is the maximum of ST minus K, the strike, and 0. And in general, for a more general option, this function phi could be completely arbitrary, but this is the standard case that we will present here. And what we need to be able to do to satisfy our client needs is to be able to calculate a fair price. What should they pay for this option? If we just look at the payoff function, it's very simple. It looks like this. It is piecewise linear, and on the x-axis here we have the stock price, and on the y-axis we have the payoff. And if the payoff, if the strike is 100, then up until the stock price 100, you gain nothing from the option. And when the stock price exceeds 100, you will have a linear increase with the slope of 1. And this graph, it just displays the recent price movements of the OMX Stockholm index. So it is the time on the x-axis and the price of the index on the y-axis. And let's take an example here, why one would want to buy an option. Let's say that we have excellent knowledge of the market, and we have a very strong conviction that when the market is at the bottom here, that it's going to rise very fast. So let's consider two alternative investments here. Number one, we just buy the index. Okay, so we buy it here at roughly 2,000, and then we plan to sell it here up at 2,600. So then we have made a nice little profit if we do that on 600 crowns, which is like what, 30% or so. But if we want to be if we want to accept a higher risk but also a higher reward, then we can instead buy an option here. This European call option, by design, it's going to be cheaper to buy the option than to buy the actual underlying product. So ballpark, if the index price is here is about 2,000 and the strike is that same value, then the option is going to cost around, let's say 100 or 200, something like that. Let's say it costs 200. And then, so you pay 200 for the option, and then the price increases from 2,000 to 2,600, and you know that, well, you had some premonition here, so that this was the expiry date of the option. Then you have gained in percentage terms a lot more from buying the option compared to buying the stock. And on the contrary, let's say that you are here and you have a very strong premonition that, oh, I think that the stock market is going down. Then you can buy a put option to protect your portfolio. Then you will earn money when the market goes down. So that is just some background on why one would like to possibly buy options. So then going back to the question of pricing, how much should the bank charge the client? So the fair price is determined by the so-called discounted expected payoff. And this expression here, so we have e to the minus rt. This is known as a discount function or a discount factor. R here is the interest rate. T is the time to expiry. And what this exponential function just does is just that it transforms some money that you are due to receive in the future and calculate the value of that today. And actually, for the purposes of this moving further into this presentation, we can actually forget about this one and only focus on the next part, which is this expected value. So we have the expected value of the payoff, which is just the expected value of maximum of st minus k and 0. Right? So this expected value, this depends on the distribution of st, our random variable, given a current price s0. Okay? Now, under the widely used Black and Scholes model, so Black and Scholes, and Merton, they got a Nobel Prize for this actually in the 90s, I believe. and this was research done in the 70s, if I remember correctly. Basically, the model says that the log of ST over S0, this is Gaussian random variable with this mean, which is R minus 1/2 sigma squared multiplied by time to expiry, and the standard deviation is going to be some parameter sigma square root of t. And sigma here is the volatility of the stock. And what is the volatility? Essentially, it is just how big are the random movements up and down of this stock. The bigger the random movements are, the bigger is the volatility. So that is that. And okay, how can we then calculate this expected value? Well, under the Black and Scholes model, it is actually possible to calculate a closed form solution for this particular form of the payoff function. For a general function, you need to resort to some numerical techniques, for example, Monte Carlo. I will show you here a Monte Carlo recipe to price this product. And this is just standard classical Monte Carlo. What you would do is that you would take the distribution of ST, and we would simulate an outcome of the future stock price, and we would evaluate the payoff. We would apply this maximum function. We would repeat this n times. We would calculate the average payoff, and that would be our recipe. And why would that work? Yes, it's because we have this fantastic law of large numbers. So the average of the phi of xi's, that converges to the expected value of the maximum function, right? And this is as the number of repetitions goes to infinity. So, what can we do on a quantum computer? So, let's start by introducing this parameter here, mu, right? Say this is the expected value that we are interested in. And the deep idea here is that what if we could encode mu into the state of a qubit in this fashion? So we have the state psi here is given by square root of 1 minus mu 0 plus square root of mu 1. Let's define a state like this. Then the probability of measuring a 1, this is going just to be the square of the square root of mu, so this is going to be mu, right? So if this was possible, then we could then just implement this on a circuit. We could run this circuit with n shots. We could measure this qubit. We could calculate the average of the measurements, and from the law of large numbers, we would again have this convergence to the expected value. So the question is this possible to do? And the answer is yes, we can do it. Then I just want to say that this scheme as outlined here, this is not really what is known as quantum Monte Carlo. This is more like classical Monte Carlo implemented on a quantum computer, and that's a very important difference. But this is a prerequisite, you could say, to actually implementing a proper quantum Monte Carlo, which is what the next speaker will talk about. So, so this is a prerequisite right here. But this idea to encode the expectation directly into the state of a qubit, this is the central idea here. So how do we do this then? Well, let's take n qubits, and we take a discretized distribution of stock price to the n grid points. We can take them to be equidistant, it doesn't matter. And then we define this pi here. This is going to be the probability of measuring I. And we can define this operator I. that acts on the zero state and just maps it to this sum here with the square root of the probability to measure I and the I state. So if we have this operator I, this encodes our probability distribution into a circuit. So we can take the log normal Black-Scholes model and calculate basically the corresponding probabilities and then just build such an operator circuit that does exactly that. Okay. And okay, so then we have added the distribution. That's a good first step. Next thing is that we need to add the payoff function, right? And we need to encode the expected value in a qubit. Okay, so let's say that we have a, let's take this situation. We have a random variable on our binary numbers here, 0 to 2 to the n minus 1. And we have some function that takes our x and maps it to the 0-1 interval. And if we have a function which does not map to the 0-1 interval, then we can hopefully just rescale it. We will come back to that. But for this recipe to work, you need a function on the 0-1 interval. And then we can define this operator f as acting on the I state and the 0 state here of some qubit as this expression, and we don't need to care about this first part of the 0 here. But the second part here, this is the key, where we have the 1 state. So we have the square root of f of I, the function f applied to state I. We have the state I, and we have the 1 here. So if we apply this function to our what comes out of when we apply the A operator to 0n and 0, then we get the following expression. We get a sum over all the states. We get square root of f of I, square root of pi. We have the I state and the 1 here. Okay. And this is where the magic happens, because when we have managed to create this specific state using the A and F operators, then the probability of measuring a 1 in this final qubit here, this is actually going to be the sum over all the outcomes f of I, pi, and this is just the expected value of f of x. So this is where the magic happens. But then, as I hinted, there's a problem in our specific case. This maximum function, it does not map to the 0-1 interval, unfortunately, but we can rescale it. So it's going to be a relatively simple rescaling scheme. We take some new function f hat of x, define it as this ratio of f of phi of x, where phi of x is just it's x min, which is we have done some discretization, so this is the minimum value, and then plus the difference between the maximum value and the minimum value multiplied by x over 2 to the n minus 1. So if x here is 0, then this ratio here vanishes, right? So we are left with the first term, which is x min. Then if x is 2 to the n minus 1, then this is 1, and we will get x minimum plus x maximum minus x minimum, so we will get the maximum value here. And then we just finish off by dividing by the f of x max. Okay. And then, as I said, the scheme that I've showed you here, it's not true quantum Monte Carlo. It is classical Monte Carlo implemented on a quantum computer. But now I want to show you how to actually do this in Qiskit. But first, a couple of references here that are central that you can dig into if you want to understand more. So Werner and Egger quantum risk analysis and Stamatopoulos option pricing using quantum computers. These are the most important ones. So let's see if I can manage to flip to the right screen here. Let's see. It should be no, not that one, not that one, not that one. No. Yeah, this one, right. Okay. So let's take a look here and see what we have. So first, this notebook is based on the work of M.Q. Lachwayo of the ENCCS. I hope I'm not butchering the name. What we have here is our payoff function, right? The maximum function. And we seek to estimate this expected value. And the first step is to, let's see if I can, I'm not used to a Mac here, so see if I can navigate this properly, but it seems to work decently. To encode the probability distribution, right? Oh, sorry. Victoria, how do I do that? Oh, yes, but I couldn't. Aha, okay. Yeah. We can try that one. Okay. Is this better? Yes. Okay, great. Yes. Bigger is always better, right? Okay. We move on with encoding the probability distribution. We need this operator, right? We want the zero state to be transformed into our prepared probability state, right? Which is defined as the sum of outcomes, square root of the probability and the I state, right? What we do here is that we import a lot of functionality from Qiskit, as usual. And then we start by filling in what is the number of qubits that we want to represent the stock price on. So here we have 3 qubits. So it means that we can have 8 states for our future price. Then we set the parameters. So we say that the initial spot price is 2 euros or whatever, volatility of 40%, 5% interest rate here, 40 days to maturity. And then the resulting parameters for the log normal distribution are what have to be calculated. So this is just basically transforming from normal distribution to log normal. And we create this low and high. This corresponds to the x min and x max from the slides, right? So basic idea is that we get the mean of the distribution, and from a probabilistic meaning, it's highly unlikely to get some outcome which is outside of, let's say, 3 standard deviations. So we take 3 standard deviations on either side, and we start the discretization there, and then we're going to get, almost 100% of the probability mass. So that is how we are defining these low and high parameters here, right? And then we have this very fancy log normal distribution from Qiskit. And we just feed it with how many parameters do we have, what is the mean and variance of this distribution, and what is the low and high, right? And then we can draw this uncertainty model. It's actually going to be a quantum circuit. So we just draw it, and then we start to think, what the hell is this? Because it's just a black box. but we can decompose it a number of times. If we decompose it 3 times, then we will see it's just composed of some 1 and 2 qubit rotations. So we can recognize what we have here, right? And then we can plot the distribution just to see what it looks like. So on the x-axis here, we have the spot price at maturity, so the final price. And here on the y-axis, we have the probability. And this has the typical log normal appearance. So it is slightly more skewed to the right. And then we can define our strike and our payoff function. So here we set the strike at some number. This is 1.896 we have taken here. And if we then plot the payoff function, it's going to, well, we're going to remember the shape from the slides. And we see this is the value that we had picked for the strike. And the payoff is 0 to the left of that, and then increases linearly to the right. Yes, so strike, it is when you buy an option, you say like, okay, I want to buy this stock for 120 sometime in the future. So you determine the price that you want to buy for, and that is the strike price. And then what you will, so then you will have the right to, when the option matures, when it expires, then you have the right to buy it for that price. But then let's say, oh, but the price in the market, what you can actually buy the underlying for, let's say that was 150. But then you can buy it, you have the option, so you buy it for 120, and then you can immediately sell it for 150. So then you have made money there. Yes, and this implementation here, it uses a comparator that flips an ancilla qubit from 0 to 1 whenever the spot price is at maturity is greater than strike, right? So that is how we keep track of that. So this controls the linear part of the function, and in the end, recall that we are interested in the probability of measuring 1 in the last qubit, because this is going to be our expected value. I think that the Qiskit documentation is pretty good here, both for this linear amplitude function and for related stuff. So I will not go into all the details in how these functions are implemented, but you can find it here in the documentation. I can perhaps just show you briefly. It's rather well documented here with some nice mathematics and so on, and also with this with a couple of references. Oh, even Werner and Egger at one point. Okay. Let's see. So we should go. No, where were we? Here, right.
There's a quick question here
yes.
from chat. In what situation would you lose money in your example?
Yes. Let's say that the stock is valued at 100 today, and then you buy an option that's with the strike of 100, and then let's say that the market falls, and when the option expires, the price is 80. Then there is no reason for you to buy it using the option at 100 when you could buy it at 80 from the market, right? So the value of the option is worthless. right? But you have spent some money. You needed to pay something to get the option. And that money you have lost because the option has become worthless. Okay. So now we will use another very nice Qiskit function. So we will go and create this variable, which is the European call objective, and it uses the linear amplitude function from Qiskit. So we just feed it with the important parameters that we have, that is the number of qubits, the slopes. What are the slopes? Well, it's 0 to the left of the strike, and it's 1 to the right of the strike. The offsets, well, there are no linear offsets in this model. The domain, this is the low and high, so the lowest and the highest price in our discretization. We have the image then, which is the lowest is going to be 0, that is the lowest payoff. And this is going to be the maximum payoff, right? The Fmax. And the breakpoints, the break happens exactly here at the strike price. So you have slope 0 up till the strike price, and then you have slope 1. And then there is an approximation factor here, which I have not told you anything about, but it has to do with the fact that you are in a way measuring when you're measuring an amplitude that you have calculated through rotations. You're really measuring the sinus of something. Yes.
Sorry, I'm a total layman to any kind of finance. But so this problem doesn't scream extremely complex to me. Could you please put it in context that how many calculations, what are we talking about as a scale? So this actually requires quantum.
Okay, so I mean, yes, actually, this example here, pricing European call option, this is the best example of a toy example that you could possibly find, because 1, there exists a closed form solution. 2, you could easily implement just classical Monte Carlo on a classical computer and calculate it. But there are some problems which are a lot bigger, where you could have, let's say, thousands of stocks and interest rates and currencies that you need to simulate simultaneously, and you have hundreds or thousands or tens of thousands of these options or other financial contracts, and you need not only to simulate like one step here. You can see it, we're just simulating the price at one point, but you need to simulate the price for, let's say, every day or every week into the future. And then when you have done that, then you need, that will give you some number. I'm not going to go into the details of what that number means, but then essentially you also need to calculate all the derivatives of that number with respect to all your inputs. So in a crude way, you would have to repeat this calculation by just bumping one of the inputs at a time, and that's going to be extremely expensive to do, and it's going to take many hours to do on the supercomputers.
We actually have another general question, somewhat challenging, possibly related to the last one. Given that options trading is often high frequency, how feasible will this be with the rather slow quantum computers that we have? Slow as in,
Well, and then coming back to the fact that this is definitely a toy example. So you have a closed form solution, so there's no real need. You don't gain anything really in practice from implementing this on a quantum computer. But yes, that is one challenge that is going to have to be solved when you want to actually solve the bigger problem that I just discussed. Yes.
I believe the example is also giving us a practical feeling about how we can transform the classical problem in the quantum state.
Mm-hmm.
Because without doing this exercise, we will never be able to approach the more complicated problem.
Exactly, I agree with that.
And the computers are developing and algorithms are also improving at the same time. So it's like two-way road. They will meet somewhere.
Yes, it's a standard case of you need to be able to crawl before you can walk, right? So definitely agree with that. Yes, moving on. If we try to draw this European call objective that we have just implemented thanks to Qiskit, then again we get almost nothing. But we can decompose it 5 times to get a circuit that we will not try to deep dive into because it's rather big. But we will at least see what is going on a general level. But then, okay, so we have 2 different circuits here. We have one circuit for the probability and then one circuit for the payoff, and then we can just combine them into a single circuit. So we create first some different quantum registers and classical registers here. And we set up a quantum circuit that contains these registers. And then we append this first, the uncertainty model, so that is the probabilities, right? And then the European call objective. Then we just get the combined circuit like this. And then we have the final measurement operator. So Q here, this is the qubit that we have encoded the expectation into the amplitude of this qubit. So this is the one we want to measure, right? So we measure that into our classical register, and then we just take the standard Qiskit sampler and run it 10,000 times, and then we get some outcomes here. So we only measure 1 qubit, so we get zeros and ones. But this number, remember what I told you about this rescaling problem that we had to do. So now we have, under the hood, rescaled the problem to the 0-1 interval, so we need to do a reverse scaling to get the actual proper result back. But first, we calculate the average. This is just the average of the measurements. And then, based on this p-hat, we can calculate standard deviation. It's just going to be the square root of p times 1 minus p divided by the number of shots. Right? And then we can use this post-processing function that Qiskit is kind to provide. So we calculate the post-processing of the measurement, or of the average measurement, and of the average plus and minus 2 standard deviations to get a confidence interval. So then we can see here that the so-called raw estimated average, it's 0.36 with a rather small standard deviation. And if we look at the after this transform, the post-processing, then we end up with an average of 0.144, which is a little bit off from the exact expected value in this case, which can be calculated as 0.16. But we see that this number 0.1623, this is within the confidence interval here, within the confidence bounds. So we will accept then our algorithm as being properly implemented. Yes, and this is the end of my part of the talk. So are there questions? Yes, so this is the expected value, right? And then you need to discount this value, and then you get the price, right?
Preparing the log normal distribution, I assume, is efficient in the number of qubits, but like like about the linear amplitude circuit, because you didn't transpile it, so I was asking myself how that circuit looked like.
Yes, but we had it, or do you mean in on a higher level? This was it, right? So it's not transpiled; it's just decomposed.
Yeah. The scales the number in time number of qubits. We are using cost function.
It's a good question. I haven't seen any numbers of that actually.
Okay. In the notebook. Okay. Thank you.
So when you discretize thank you for the talk. When you discretize the stock market, so you use n qubit.
Yes.
So the number of qubit, how it affects the accuracy of this procedure or the coding.
Yes, it's going to have a very big impact. So I mean, the grid that you will get is going to be rather sparse, right? So we had it here. We have only these 8 possible values, right? But that's very simplistic. So in practice, to get an accurate representation, you need quite a few more qubits.
What is the time scale to run this type of code? How long it takes?
How long it takes?
Yeah, for just this simple code that you.
I mean, it takes longer than calculating it classically. That's for sure.
Thanks.
I think we're having audio problems with our mics, maybe. Now it sounds okay. Okay, any more questions? One in the chat. Excellent. And I will read it out. Any comparison with pseudo-random number generation?
Yes, I guess on this is another interesting difference here then between classical Monte Carlo and Monte Carlo on a quantum computer. So on a classical computer, of course, you cannot have true randomness. It's not possible. You only have pseudo-random numbers. But in this implementation, if you're running this on proper hardware, which is going to be difficult today for other causes, just hardware problems. But then you will actually have true randomness. So maybe that is something that will give this an edge. Who knows? Especially in high dimensions, it can actually become a problem in classical simulations.
Very good, thank you. So what happens now? Are we doing a hands-on, or are we're not up for a break?
It depends on if Victoria wants to start right away or if you want to have a break first.
So Bjorn showed us how to price options, both with classical Monte Carlo and also classical Monte Carlo on a quantum computer. now the question is, can we do better with quantum? And what I will try to present here is quantum amplitude estimation, which is a way that at least, it's an algorithm that at least theoretically provides a quantum advantage to classical Monte Carlo, theoretically, and yeah, we'll see. So picking up where Bjorn left us, we saw that we can price options, we can compute expected payoffs of options using Monte Carlo by sampling independent and identically distributed samples from the underlying at the final time at the expiry, and then computing the average, right? And by the law of large numbers, that estimate will converge almost surely to the value that we try to estimate. And moreover, the central limit theorem gives us a bound on the expected error of that estimate, and we see that that bound is of the order of 1 over square root of n. So this is actually good because it doesn't depend on the dimension of the estimate, but it's not a really quick convergence, right? Now the question is, can we do better with quantum? And the answer is yeah, kind of, sort of. We'll see. How we can try to do that is we can try to construct a unitary operator acting on a register of n+1 qubits, like this. So here the amplitude of the state 1 on the n+1th qubit is a, square root of a. So the probability of measuring 1 in the last qubit is a. And if we can construct a in such a way that it somehow relates to the quantity that we try to estimate, then if we're able to measure that a, then we've found a way to price the option, right? Can we estimate a? So quantum amplitude estimation does just that. It's an algorithm to estimate that amplitude. That's what I will try to present. But first, some preliminaries. Phase estimation is an algorithm that is sort of a simplification of amplitude estimation that will serve as a motivation for the algorithm that I will present. So the setup for phase estimation is that we have a unitary operator and a known eigenvector psi with a unknown eigenvalue that we try to estimate. And it's unknown, but we do know that it lies on the unit circle because it's a unitary operator. So then we can write it in this way. And it will be obvious why we do it like this in a second. The task is to estimate lambda. So it turns out that if we build up this circuit, here we start with a zero state on n qubits, and then here we have the state psi. We put some Hadamard's on the ancilla qubits, and then we apply successive applications of control U gates controlled by the ancillas. Then after that we do a inverse quantum Fourier transform and measure the ancillas, and it turns out that the integer that we measure here will be an estimate of Q, from which we can recover lambda. The theorem is like this. So with probability 1 minus delta, the estimate Q tilde provided by the phase estimation satisfies the server bound, which is of the order of 1 over n, where n is the number of quantum samples, 2 to the number of ancillas. A proof idea is not really a proof. It's just a motivation for why this Q is actually an estimate of why this Q tilde is an estimate of Q, but for a simple case where Q is an integer. So if Q is an integer, then we can go through the circuit here and see the action of the different gates. So yeah, let Q be an integer. from 0 to the power of n minus 1. And then if we just run through the circuit, first of all, we apply the NCCS to the, we apply the Hadamard gates to the NCCS, and we get this superposition state. After that, we apply the control use, controlled by the NCCS, and we get this state here. The main point, the main idea going from here to here is to observe that psi is a eigenvector of u. So every time you apply u to psi, you just get this to a certain power. And just move things around. This is what's called phase kickback. But to me, this is just like putting parentheses and moving things around. But we have a fancy name for it. So now the phase of the lower qubit has somehow affected the phase of the NCCS. And we can observe that this is actually, in fact, the action of the quantum Fourier transform on the integer q. And this is the main observation of phase estimation. So now, last step, if we apply the inverse Fourier transform, then we end up with what I was claiming, right? This is what I wrote here. This is the observation that this is precisely the action of the Fourier transform on the integer. And that's the conclusion. And once we get Q, then the eigenvalue can be recovered as like this. Note, as I mentioned, well, no, I didn't mention, but for Q, an integer, then we actually recover an exact estimate of Q. So we introduce no error. For the general case, like the theorem that I showed, then it's a bit more complicated. You need to do some error analysis. Not a big deal, but it's a bit more cumbersome. So you can see one of those two papers for a proof. So with that out of the way, let's introduce amplitude estimation. Same setup as before. We have a unitary operator U acting on n plus 1 qubits like this, and we're trying to estimate A. Yep. So amplitude estimation uses a combination of phase estimation and amplitude amplification in order to get an estimate of A. And it works like this. So it's very similar. It looks almost the same to phase estimation. But a couple main differences is that here we have M NCCS, and we have n qubits here for the state, n plus 1, and we start with zeros everywhere. And then we apply Hadamard, and then we apply control applications of this Grover operator. And this Grover operator you construct with these two reflections. This is a reflection against around the psi sub 0, which is this state right here. And this is a reflection around the 0 state. So then you measure Q at the end in the NCCS and map it to an estimate A in this way. So you construct this angle like that and take the sine squared of that angle, and that will be an estimate for A. We have a theorem for that. So with high probability, 8 over pi squared, which is around 80%, 81%, the estimate A tilde provided by amplitude estimation satisfies this error bound, which is of the order 1 over m, where m is the number of quantum samples. So here, if we think about it, then we got a quadratic speedup over classical Monte Carlo, right? So for classical Monte Carlo, we had 1 over square root of n. Now we have 1 over m. That, at least theoretically, is a quadratic speedup. That's what I'm saying there. Yep. In practice, since what you have here is you just have this bound with high probability, what you do is run QA a few times and take the median value, and then this will give you a success probability as close to 100% as you want to get. A proof idea, again, it's not a proof, but a motivation. The main part of the proof is to use the phase estimation theorem that I showed before, and then observe this fact, which is that this Grover operator acts on U like this. So in particular, the probability of measuring P, the probability of measuring 1 in this state is the sign of 2k plus 1 on the theta A, where theta A is this arc sign of square root of A. So if you take this fact and apply the theorem from before, go through the circuit, and then you'll get the error bound that I showed. So a toy example, we can let U be a Bernoulli random variable with success probability P. So you can think of this as a one qubit circuit from which, if you measure, you will get 0 with probability 1 minus P, and you will get 1 with probability P. And that can be modeled really simply with a rotation around the y-axis of this angle, theta P. And the Grover operator for that case is also very simple. It's just a rotation of twice the angle. Moreover, the powers of that Grover operator are also quite simple. So the kth power is just a rotation of k times the angle. So it looks something like this. You can construct it in Qiskit. Here, what I call A there is what I was calling U before, but then you can apply the Grover operator controlled by the ancillas, do the inverse Fourier transform, and then measure. I have some code. I will go through this again, so it's not you need to follow super closely. But with this object here, you can given the straight preparation circuit, so the U in the slides or the A in the circuit that I showed, given a number of ancilla qubits and given which is the objective qubit in the state that you want to measure, then you can construct this circuit. So we can quickly go through it. You initialize the state with you initialize the circuit with an ancilla register, a register for the state, and then a classical register for the measurements. Apply the Hadamard's, these Hadamard's. Construct the Grover operator. You can construct it like this. I'm just using Qiskit's function for the Grover operator. And apply control powers of that operator. And finally apply the inverse Fourier transform and then measure. We'll see this more closely later. Okay, so you can apply amplitude estimation to this toy problem, and here we have the estimate. So this is the number of quantum samples. So here we have one ancilla, 2 ancillas, 3 ancillas, and so on. And we see how we converge quickly to the real value of P. Here I was using P equal to 0.75. And the gray area is the error bounds, the 81% error bounds above and below. So now we saw the toy problem with this binomial distribution. We can try to tackle the derivative pricing problem. So Bjorn showed us how to construct a circuit where A represents, after some rescaling, the expected payoff of the function. And it looks something like this. We had a black box representing the uncertainty model, and we had another black box representing the payoff function. So we can try to approximate A with amplitude estimation. The circuit looks like this. we have the state preparation circuit here. This is the whole circuit that Bjorn constructed, both the state preparation and the payoff function. This is encoded in A, and then compute the Grover operator and apply control applications of that operator. And we can go to the notebook. So here, if you're seeing this on the web page, I think there were some rendering errors. Here, so you need to go and separate the double dollar signs by white space above and below. Sorry about that, because I didn't know that in VS Code it doesn't happen. So this is the same notebook. We stopped here with Bjorn's presentation. Now I'm picking up from here. This is a little bit of theory, more or less what I've been talking about. So we get, this is the European call circuit that we had from before. We construct the amplitude estimation circuit like I showed with 7 ancillas. And now we see the depth of this circuit is not very promising, right? You can think about, okay, A had already a bunch of gates. Q had more gates than A, and then you're applying Q to the power of 1, then you're applying Q twice, you're applying Q 4 times, and so on, so that grows pretty quickly. So for 7 qubits, you get 500,000 gates. So yeah, theoretically we get a quadratic speedup, and we do see that on the simulations. But of course, if you do that on real hardware, you're gonna get noise. But we can run this on the simulator. Here I'm gonna run it 100 times. As I mentioned, you normally run it a few times and then take the median value in order to get the success probability of close to 100. So we can run that. I think well, in any case, I have all the results here. So we run it, and when we can do the post processing. So here I'm basically doing this. Maybe I can go back. But I'm doing this. Take Q as the measurement of the ancillas, construct the angle, and then take the sine square of that. This is all the post processing. And then I'm also combining the duplicates, because when you take the sine, then you're kind of taking some of the integers that are different end up folding into the same values when you take the sine, and then take the mode, the estimate with highest probability. So we get 0.175 more or less, which we see lies within the confidence bounds that we computed before. Okay. We can do the same thing. We can see how the estimate converges as we increase the number of ancillas. Here I'm plotting the estimate before the rescaling. So we saw that A is a value between 0 and 1, and we need to scale it to the actual value. Here, just so that these confidence bounds make sense, I just plotted the value before rescaling, and we see that we converge pretty quickly to a value. Okay. So I think most of you already know the answer to this question, but is QAE NISQ ready? Is it ready for noisy intermediate scale quantum computers? Well, this is how the number of gates grows as we get more and more ancillas. For the toy example, for the binomial, for the other one it's even worse, but it grows pretty quickly. As far as I know, the best we can do today is about 1,800 gates on IBM Heron. So we would only be able to run maybe with 4, 5 ancillas. So yeah, maybe QAE is not the way to go today, but all hope is not lost, I would say. There are other versions of quantum amplitude estimation that attempt to solve this issue. I think maybe the most promising is iterative amplitude estimation. It's quite a complicated algorithm, but the main idea is to, instead of running circuits with so many ancillas, you somehow run the circuit multiple times, and you can get closer and closer to your estimate. This one, maximum likelihood amplitude estimation, is just a little twist on what I did. It's all basically the same, but instead of taking the mode, you do a maximum likelihood on the estimate, and you can get a bit more precision there. This one, I don't know exactly what they do, but they claim it's faster, so I guess it's worth a read. Here we can see convergence rates of different versions of amplitude estimation. So the blue line is classical Monte Carlo. So we see a slope of -1/2. Then that represents the convergence rate of 1/√m. And then all the other lines are different flavors of amplitude estimation. And they all have slope of -1, representing the convergence rate of 1/m. So for example, canonical quantum amplitude estimation is the gray line over here. Iterative amplitude estimation, different versions of it are over here. Yeah. So conclusions, we get a quadratic speed up over classical Monte Carlo, at least theoretically. And this can be useful in different areas of mathematical finance where Monte Carlo is standard, such as derivative pricing. It's not NISQ ready, but it's an active area of research, and maybe as quantum computers get better and better, this can prove useful. Some more papers on quantum finance. This is the main paper I've been following. And they not only talk about call options, European call options, they also talk about more complicated options such as baskets and path-dependent options such as Asian options and stuff like that. This second one, they price Asian and barrier options under the Heston model. So with Bjorn, we saw that we were using the Black-Scholes model, for which we get a log normal distribution of the underlying. And there are more complicated models, such as the Heston. Yeah, this paper deals with that. This shows how to load arbitrary distributions into the state preparation circuit. For our case, we had a log normal distribution, which was somehow simple to implement into the circuit, but you can have more complicated distributions, and you can do that with a quantum generative adversarial network. And I had to mention this. This is Bjorn's paper from last year on a slightly different topic on quantum finance or quantum applications for insurance. It's also worth a read. So this is all the reference that I've been mentioning, particularly this one, pretty important for our work. And that's it. That's all I had prepared. Any questions? Any comments? Otherwise, we'll go into the exercise session that Wilhelm has prepared for us.
Probably everyone is eager to see the hands-on.
Okay.
So let's go.
Let's go.
Yes, my name is Wilhelm Mågren. I work together with Victoria at Handelsbanken. And if you go to the GitHub IO page for the second day, you can find the tutorial notebook uploaded as it is on here. I noticed there were some markdown LaTeX math input errors here because it doesn't like the euro sign. We had the euro sign for a simple example. But if you just download it, it's going to look fine. And what we had planned for, I guess, the next hour is that you're going to get an hour for yourself or for the people around you or together with us to do this hands-on. And we want to emphasize that you should not be stressed when you take a deep dive into this. Take your time and try and understand all the nuances. But first, just to get you kind of more into the mind of this, I thought we could go through a brief example because options are not super intuitive when you first hear about them. Hopefully this might clear up some question marks that you have. So we're gonna go with the example with Alice and Bob. And let's say that Bob is the bank in this case. He's gonna sell an option with the underlying stock as IonQ. I thought was quite fitting for this occasion. And let's say that the spot price today is 30 euros. And for some reason, Alice, who wants to hold this, buy the option, says that in 30 days, I want the strike price to be 35 euros. And Alice and Bob, they agree on the premium of the contract to be 5 euros. So Alice has to pay Bob 5 euros to engage in this contract that in 30 days, if the price of IonQ is above the strike price or equal to strike price, is gonna make money, which is the actual price of IonQ minus the strike price, right? Which Björn showed. And just some example cases here. So let's say Alice, she's a real finance genius, and she knew IonQ was gonna go up in price. And fast forward 30 days, and it just so happened that IonQ is trading for 50 euros. Then the payoff is gonna be 50 minus the strike price, which was 35. So she's gonna make 15. But remember 30 days ago, when she engaged in the contract, she had to buy the contract from Bob for 5 euros. So, the payoff is 15, but she had to pay to engage in this, which was 5 euros. So she's netting 10 euros. And as Björn also said, if IonQ is trading for less than the strike price, then there's no reason to buy the option. And it's important to emphasize that the buyer has the right, but not the obligation to exercise the contract. So she would not exercise in this case, and the option is just worthless. And so Alice, she has already paid the contract, 5 euros. And so Bob makes money on the contract, Alice loses on the contract. And in between there's a bit of a gray zone because the contract is 5 euros and the strike price was 35. So let's say that the IonQ is trading for 38. Then Alice is gonna make 38 minus 35, which is 3. But remember that she had to pay €5 upfront to engage in this contract. So she's actually not making any money in the end. Hopefully that cleared a bit up. But so this notebook is divided into these 4 sections. So first, just a quick reminder, which I guided you through here, on what the European call option is. And then you get to load the and play around with the distribution of the asset, and also how to encode the payoff function. And then you're gonna get to do the classical Monte Carlo on the quantum circuit, and then finally quantum amplitude estimation. And I've tried to highlight all of the exercises with this pen and paper emoji, and emphasis on the exercises just to play around with all of the variables, see how the circuit changes, how the distribution changes, the payoff changes, and so on, and try to build your own intuition on how you can use quantum circuits for this kind of problem. And I'll be here in the room, Victoria's here in the room, Björn is here in the room. So if you have any questions for the coming hour, just grab us. We'll try and help. Yeah.
Very good. So we all get to finally focus a bit in peace and quiet and learn something about this interesting use case. So let's get to work. And for people online, don't hesitate to raise any questions, any technical issues, whatever you might have. Raise it in the chat or in the HackMD document. So, and Wilhelm, this is necessarily done on a classical simulator, yeah? So please go ahead.
Okay. Yeah, I hope you're still awake, the audience. I can't see you very well, but yeah, you have to listen to me the next 30 minutes. So, and I will tell you a bit about the Quantum Sweden Innovation Platform. I'm the co-director of this platform, abbreviated QSIP. And yeah, if we consider the landscape in Sweden with regards to different initiatives related to quantum, we can see some of the more pronounced here. It's VACT, which is a large research initiative financed by the Wallenberg Foundation, which has been financed by about 1.5 billion Swedish kronor, yeah, 150 million euros. We have ENCCS, which you know all about. We also have the Wallenberg Initiative on Networks and Quantum Information, the WIN-Q. We have the National Quantum Communication Infrastructure Project, which is EU financed. The Swedish Quantum Life Science Center, which is focused on life science applications for quantum. And we have also at KTH, the Royal Institute of Technology, has its network, the QTH. And now I will introduce to you Quantum Sweden Innovation Platform. And Quantum Sweden Innovation Platform is something that has as a major objective to stimulate, foster, and promote quantum tech innovation in Sweden. We have, as I pointed out, there has been a lot of excellent research going on in Sweden since at least the last 20 years, but with VACT, for instance, since 2018. And these efforts have produced a large number of competent researchers, very interesting research results, and in some cases also business ideas. So taking the next step and to bring these into innovations and commercialization is something that Quantum Sweden Innovation Platform would like to contribute to. And of course, in the long run, the emergence and growth of a Swedish competitive and attractive industry, both within quantum technology, but also by applying quantum technology in the existing industry. And yes, we're a pretty recent effort. We started about 1 year ago in November 2023, but it's intended to be a 10-year effort. I represent Chalmers Industriteknik. That's where I'm employed. But I spend most of my time working for a QSIP. And you could also see the major partners and financiers of the platform. It's of course the major universities involved in the research in Sweden, because quantum is still very research oriented and still close to research facilities, although we're taking the first steps towards the applications here in Sweden. What we've done during the first year of QSIP is to establish the innovation platform to verify the benefits and the needs of the platform. These are some of the tasks. Of course, providing basis for a national commitment and coordination in quantum tech innovation, to support the formation of a Swedish ecosystem within quantum tech innovation. The international visibility and collaborations and interactions, that's a very important area of QSIP to promote. Increasing quantum literacy, it's of course important that not only the researchers know what quantum is, but also, of course, many other organizations in society need to know, of course. And here we can see a mission for us. Of course, Sweden is a relatively small country, so in order to really create synergies and take fast steps forward, we need to coordinate the innovation efforts in Sweden with other deep tech arenas or areas such as semiconductor design and similar. And of course, make sure that Sweden is involved in policy work and standardization is also an important task. And looking into what's really important for innovation is, of course, in this area, access to infrastructure, test beds, and components, capital, competence are very important ingredients to achieve innovation and scale up. During 2024, we've had lots of activities. We've arranged 2 thematic half-day workshops, one on quantum communication and one on quantum security, quantum and cyber security, sorry. We have formed a Swedish investor network in order to increase the competence level among Swedish investors, but also, of course, to enable co-investments and lowering risks of investors in this field. Because, investing in quantum technology, you need to be patient, and it's still some way to get to the market for many applications. We've arranged 3 Swedish delegations, mainly with startups, to international conferences like the IQ Nordics in Helsinki, the Quantum World Congress in Washington, D.C., as well, etc. Here we've had exhibition booths where the Swedish quantum startups could exhibit free of charge, and also have, of course, arranging business meetings with international partners together with them. We had webinars in different areas. We've had international initiatives presenting their activities in quantum to the Swedish audience. We arranged a QSIP conference day with more than 80 participants. And we have established some really tight and good collaboration activities with the innovation ecosystems in some countries so far, Denmark, Finland, and Netherlands particularly. So I think we're pretty well on our way. And these are some examples of activities that we have. I mentioned that we have most of the universities performing where you have quantum research going on. And mainly it's their innovation offices participating in QSIP. And of course, in order to improve the services to researchers, to take research results to commercialization. It could be via startup. It could be in terms of a large collaboration project with a potential user or a large company. And so we have a startup support process with the innovation offices in order to proceed rapidly. We also have courses, educations, for instance, related to entrepreneurship for academics. Really, the researchers that would like to spin off companies based on quantum results. But we also have courses, educations for startups. Here we involve Business Sweden, which gives courses on business development and internationalization, because it is an international market for the startups being active in this field. Yeah, I mentioned these workshops. I just proceed. I also mentioned the Quantum Sweden Investor Network, where we providing an interface to the startup environment in Sweden for investors. And also, of course, an interface for the startups to approach investors. Something that will launch tomorrow. So this is, you're one of the first to hear about it, but it's a quantum innovation competition, which will open tomorrow. And here we are asking for solution providers to propose potential solutions, either based on quantum technology or enabling quantum technology for use cases. And this you can find more information about on our website. And the winners can, of course, win some project funding for financing a feasibility study of their proposed solution or idea. We have monthly webinars. These are some of the Swedish startups that have presented their experiences on the way to market. This you can find on our website if you would like to connect to the Swedish SMEs in the field. So this is a way for making them visible to internationally as well. Yes, we had a delegation, a Swedish delegation going to IQT Nordics in Helsinki this year. And here we had a Swedish pavilion for Swedish startups, of course. And we try to support Swedish startups to be able to reach out and be present at these events. And actually, next year, Inside Quantum Technology Nordics will be arranged in Gothenburg, May 20th to 22. And yeah, please save the date in your calendars. The first version of the program will be published on the website of IQT Nordics within a week. That's what I dare to promise right now. But it's of course not so much research oriented as technology and application related. So many of the companies active in the quantum world will be present. Yeah, some activities that we are already scheduling is of course some webinars. December 18th, we have a webinar which is relevant for researchers and startups. How to balance when you go international. How can you safeguard your assets? How do you ensure that you're following legislation policies in this area? And on the same theme, we have in January a webinar on export control together with the Swedish Inspectorate of Strategic Goods. This is also something which is of relevance for researchers, for startups. I mean, the changes and the geopolitical changes, as we put it, makes it very important to be aware of the legislation here. So these are some activities already scheduled, and that's. I just wanted to give you a glimpse of what we're doing. You can get more information on our website. You can follow us on LinkedIn. And of course, you can participate in our activities. Many of them are online, but it's also possible to join our physical events, of course, because it's normally we're open to all participants. Okay, but I would say thank you for your attention.
Thank you very much, Johan. We do have at least one question.
Please go ahead.
Thank you. Totally stupid question, but a webinar about safeguarding Swedish assets on December the 18th. Will that be in Swedish or in English?
It will be in English.
Perfect. Thank you.
We try to arrange most of our activities in English. Yeah.
Yes. Okay.
Are you logged into LinkedIn?
Sorry?
Are you?
Good? Yeah? This is working. All right. Sorry about that. Yes. So my question is, this investor network, is this funded within QSIP as well? Or is this from external funding?
I mean, it's something we arrange from QSIP, and for arranging it, we're using the QSIP funding, yes. But of course, it's not that we're taking any fees for participating. We try to have some matchmaking events where startups or even you could say innovation projects from universities could meet and pitch for investors. That's something also we have on our activities list. So, but normally it's financed by the funding we have from Innova, for instance.
Very good, thank you. Let me check if there are any questions online. Yeah, so could you elaborate a bit on the application process for the quantum innovation competition? What does it entail?
Yeah, it will be published tomorrow on our website, and it's basically a few pages form where you describe your proposed solution. And I should mention the innovation competition closes, and that will also be on the website mid-January. So there will be a bit more than a month to formulate your proposal. But there will be a form for, to fill out for your proposal. And there you describe the proposed solution, in what sense it's can actually provide improvement compared to existing solutions? In what areas you see the use cases and potential positive effects? What is the status, of course, of your proposed solution? And so on. So it is a few pages form that is to be filled out, and you can find it on our website from tomorrow. Yeah, that will be it. And from the submitted proposals, a number will, some of them will be qualified for a pitch event, which will be held on January 29 at a big investor event in Gothenburg. It's Go West with about 1,000 investors present. So it's a big investor event. And it's a way, and at this investor event, which is a 2-day event, there will be a certain focus this year on deep tech, investing in deep tech, and particularly in quantum. So we took the opportunity to show that there is actually a lot of interesting innovation going on in the area by having the pitches at the event. And there will also be a prize award on January 13th at the same event. So yeah, that's the schedule for the innovation competition.
Very exciting. I hope someone listening considers this to be a good challenge. And
yeah, and of course, tomorrow there will be a description of the challenges as well.
Yep.
That should be addressed. Yeah.
Okay, any final questions? If not, let's thank you on again.
Thank you.
And it works. Thank you, Tor. Yes, I am the last one. Yes, before the dinner. So I will be on time. And I'm going to talk about the, say, very specific application of quantum computing, and namely, which is related very closely to us. And yes, I will tell why. And yeah, and what we can do about it. So essentially, we know that quantum computers, they can break many things, a few things in the internet, which we are using today already, basically every time we connect to the internet. And we will go through more details, about how they and why, and eventually what we can do about it. Okay, what is cryptography? We start with some basic examples. What is the purpose of cryptography? It's essentially to make data obscure. So, and you have something to start with. Let's say you have hello, which we call plain text. Then you use a process called encryption to produce something which we call ciphertext. The ciphertext is something which you can read and you can store. It will be important later, but you do not understand. So, and the idea is that you cannot get back easily. The reverse process is called decryption. It uses also a key. And then when you take this ciphertext and you convert it back to the plain text so that you can read it. So, well, there are two keys, and you may ask whether is it the same key or are there two different keys? And it actually can be both. So, and when the key is the same, we call it the symmetric cryptography, and we use the same key to encrypt and decrypt. And it's the encryption algorithms based on symmetric cryptography they're compact and they're fast and they're used everywhere, every time we connect to the internet. An example of this algorithm is advanced encryption standard. And this group of algorithms is considered to be, in principle, safe against
quantum computer attack. But if the keys are not the same, so you can also build cryptographic tools, encryption and decryption algorithms based on that. And in this case, it's called asymmetric, or in English, it's public key cryptography. And for that, you need two keys. And one of them we call private, normally which you keep for yourself, and another one we call public, which you normally share with somebody. This type of cryptography, it normally produces larger keys, larger ciphertext. It's also slower than symmetric cryptography. And it's used not so much as for the data exchange directly, but it's used for exchanges keys to have a so-called shared secret. For further use for the symmetric cryptography, or it's used for digital signatures. So if you're familiar, and for example, if in your country there are like bank applications which use signatures like digital signatures like Bank ID in Sweden, that's exactly where this is used. So you use these public key cryptography to sign your digital transactions. Examples for that is Rivest-Shamir-Edelman RSA algorithm and elliptic curve cryptography. And these two, exactly these two algorithms, they are omnipresent on the internet and they are not safe against the quantum computer. So before we go further, we just summarize what is vulnerable. Essentially, all the data exchange which uses these two algorithms, even as a part of a protocol, is at risk. It includes data exchange, direct data exchange using RSA or elliptic curve cryptography, which is probably not that usual, but mostly key exchange and digital signatures, which normally initiate the process before you start exchanging information over the internet. Okay, why is it vulnerable? If you take the example of RSA, so it makes use of prime numbers. So, and the prime numbers, as we know, is the one which we can divide by itself or by one and nothing else. And you will need two these numbers, which will be eventually used to derive keys for encryption and decryption protocols. This product of it is called N, and it's a public part of, you will produce two keys, essentially key pairs, and N will be in both of them. Okay, and if you manage somehow to decompose this N into two original prime numbers, this process is called factorization. And de facto, it means if you have managed to factor out two used primes, that you have broken the algorithm. We can try it ourselves. So 15, if we have N equals 15, what will be P and Q? And it's very easy. So if we take a look at the table up there, so it's 3 and 5, right? It's not that difficult. So let's take a more complicated example, 77. Can we tell which numbers we used? Prime numbers, right? So it's obviously 7 and 11. If we take something more advanced, like a 9-digit number, then we will need a computer. But this will go also very, very fast. So it will take you probably milliseconds on a regular laptop to factor out P and Q in this case. And this number is not actually that small. It has 9 digits, or as a binary, it has 26 bits. So far, it doesn't really feel safe. I mean, 26, can we do 50 bits? Maybe we can do 100. Maybe it will not take millisecond, maybe it will take 1 day, but who cares, right? Okay, to get a better feeling on the whole thing, let us take a look at the strength of modern security. So we take the standard today, 128-bit security level. What it means that you need to go through 2 in power 128 numbers to break the security. It's an equivalent security. It means different algorithms might need a different number of bits to achieve that. And for RSA, it means that you need 3072 bits. So the question is, is 128 bits, big enough. Okay, let's take a look at this problem. Probably you've seen this or heard about this problem before. In English, it's called wheat and chessboard problem. It's when you have a 1 grain, you put on the first square, on the second you put 2, you double it. The next one, so it will be 4 grains on the third, and 8 on the fourth, and so on. And the question is, how many grains they will be on the chessboard? And intuitively, we might think, oh, but this will be just a sack. We just kind of take it with us home. But in reality, it will be quite a big number. So, and if we assume that each grain is about 60 milligrams, then the total weight will be about just a bit above 1 trillion tons. So it will be quite a big bag to carry. But that was 64 squares. What about 128? Assume that we have a fixtures board with 128 squares, and the number of grains will be astronomical. And the total weight will be also astronomical, which we can, I would say, recalculate in the amounts which are more easy for us to compare, like it will be about 10,000 suns. I've checked it a few times, might be wrong, but it looks correct. So it's about 10,000 suns. So it will be such a big pile of grain, and which weighs 10,000 suns, and you will need to go through each grain to break this security level. So currently, at this moment, I guess it feels a little bit more safe. It's quite an amount of grains you need to go through to break it using a classical computer. And that's very true. It's estimated that if we collect all the computing power of the world, including ENCCS to get included, so it will take many ages of the universe to break it. So it's difficult, it's impossible for today's classical computers. So was that before this happened? And it's very fortunate that I don't need to explain that to this public. So it's rather another way around. So, and the quantum computer can break it within a polynomial time. And I will tell a few words about it more a bit later. I don't know, perhaps this information about the state of the art a little bit outdated. This is the data I have from last year, so that's the power of qubits we have today. I guess more important, say from, I would say, is the cost. I mean, it's a pretty expensive thing to run. So, and it's probably, I would say, will be, for if you take a regular citizen and think about our digital signatures, and it probably will not make any sense to spend that much amount of money to impersonate some, you know, of regular people. So for this, from this perspective, it feels more safe. Okay, why it can break, the quantum computer can break the current security. Because already 30 years ago, by Peter Shor from Caltech, MIT. So he invented an algorithm specifically for the quantum computer, which can do exactly what we have been trying to do, to factor out large integers and find discrete logarithms and effectively break the both RSA and NCC public key encryption and do it in the polynomial time. And polynomial time in this context means essentially we talk about hours or days, not the ages of the universe. It's worth mentioning that there is another algorithm which was invented just 2 years later by Love Grover from Stanford, and it was originally created to speed up search in unstructured data, and it weakens the security of symmetric encryption. The symmetric encryption, which I mentioned before, which uses the same key, and but this is very, very easy to fix. It speeds up, but not that much, so it's not fixable. Well, how can we protect digital assets against the quantum computer? I think it missed a few slides. Yeah, no, but okay, what can we do about it? Well, it seems natural. So we need to develop standardized cryptographic algorithms which are not breakable by a quantum computer. And there is a definition for that. It's called post-quantum resilient algorithm, simply a post-quantum algorithm. It's based on different mathematical constructs which are believed to be quantum safe today. And we need to migrate to those algorithms. And it might seem to be like, well, migrate, but that's not that easy. So, okay, how soon we need to worry? And this is an important aspect of the whole thing. The data, the session, if you remember, I mentioned that the encrypted data can be recorded, even if you don't understand it. So if you record the sessions of today, you might be able to break it in 20, 30, with time, you can break it in the future. And effectively, and also it means that we need to start the transition today, because we're probably not talking about us, but think about the today's children, and they have sensitive records, and for example, medical records which can be recorded. And if they are recorded in 20, 30 years' time, then these records, if broken, they will constitute I would say, a good foundation for for example, ransomware attack. So I would say consensus today that we need to start the transition right away, even though the computer, what is called the cryptographically relevant quantum computer, is many years ahead. It's basically to start protecting the data of today. Yeah, then always a question, when do we have a quantum computer of the sufficient power? Well, and here it's very, I would say, essentially how people do that. They ask a number of experts, what do you think, what is the, say, how likely it's that with the likelihood of 50% of more, there will be a quantum computer which will break modern RSA 2084 in 24 hours. So, and I would say the consensus is, I would say, based on this data, is that it will happen from, say, 50, slightly more than 50% of the experts think that will be within 15 years, and 84, a larger proportion of the experts think within 20 years. So it's some time to wait, but it's not that far away. Okay, and in more details about what can we do about it. And so, as I mentioned, we need to develop, standardize, and migrate to the algorithms that are resistant to a quantum computer. And the American National Institute of Standards, NIST, it started the competition already in 2006, which was completed this year, recently. And there is essentially a centralized effort. There is on the national level, there is a security memorandum having as a goal for the United States to mitigate as much as quantum risk as possible by 2035. And there has been a National Cybersecurity Center, which is a centralized authority helping private and public actors in the US to make this transition. There is a cybersecurity suit, say, issued, which are kind of guidelines for the transition for all, say, public actors in the US. What happens in EU? It's not that well centralized and organized, and there have been reports from the European Agency for Cybersecurity and about the possibility of post-quantum cryptography. And there have been different recommendations from different experts groups. And in April 2024, the European Commission issued guidelines, essentially making the member states to come up with roadmaps for transition to the post-quantum cryptography, saying that in 2 years, every member state should have a transition roadmap. So there has been more activities which we have observed for the last year, and it's just we haven't yet summarized them, so we're trying to keep a track on them. And of course, there is a lot of activities also in the standardization bodies, because I will talk a bit later. Recently, the algorithms have been standardized. First algorithms known for post-quantum cryptography were standardized, and they started to kind of propagate across the standardization bodies like ETSI, IETF, and ISO, and IEEE, and CEN-CENELEC, which is not mentioned here, and also the national standardization bodies, also in Sweden. More about the standards. These results on the NIST competition from 2006, which lasted, well, 8 years. And the first standards were released just in August this year. And there were one algorithm standardized for so-called key exchange or key encapsulation. It was originally called as Crystal Kyber and standardized as LM-CHEM. And there are more candidates under consideration in the 4th competition round. And 2 of the 3 finalists have been also standardized. This happened at the same time for digital signatures. It's crystals, dilithium, and Sphinx. And there is another upcoming algorithm. So we have now one standardized algorithm for key exchange, which is resistant to post-quantum, to a quantum computer, and we have 2 for the signatures. At RISE, we've been working with homomorphic encryption, which is actually an algorithm based on the same principles as the Crystal Kyber. And it just happened. We used it for privacy applications in particular, but it happened that actually it has all these similar properties as the Crystal Kyber. It's not yet truly has the label of post-quantum safe, because some tests haven't been done, but we hope to do them in the future. So we will have a powerful tool for privacy like homomorphic encryption. And homomorphic encryption, if you don't know, this is type of encryption which allows you to perform operations on the encrypted data. So you don't need to do it with the plain data. So you can do it in the encrypted, say with the ciphertext, and basically the results of these, like to basically decrypt them to the plain text. So you can do, for example, machine learning in fully encrypted form with the homomorphic encryption. So just to mention certain few challenges, we, as I mentioned, the RSA and the elliptic curve cryptography, they are everywhere. And we basically need to change them everywhere. So we need to, in certain cases, we need to integrate it with existing protocols and existing systems. Standardization is going on, and there are performance issues. They are more heavy, they on resources than the existing algorithm. So basically, in many cases, you will need to make compromises in certain systems when you replace the new algorithm, the old algorithms with the new algorithms. There are some issues about security proofs for the new algorithms, and there is a possible transition path. For example, to use double encryption in signatures. It's essentially when you encapsulate one into another. So you have one layer of the old, for example, the elliptic curve algorithm, and then you have on the top of it, you have a post-quantum algorithm like Kyber. As I mentioned, in the US, there is essentially there is a cybersecurity center of excellence for supporting the transition. And we say in Sweden in particular, and there is RISE, there is Karolinska, and together with EU partners like our, say, sister institutes in Finland and VTT and TNO in the Netherlands. And also with a number of academy industrial partners. So we are currently at the stage, so we need to spread the post-quantum awareness and trying to scale up the knowledge. And also specifically, we work with understanding where it needs to be upgraded first. So where we should put our resources and identify how this can be migrated and what kind of toolbox we need to use. It covers the sectors of telecom, health, energy, space, and the data spaces, which is a EU thing for exchanging the data. So I think that was it. Thank you very much.
Thank you very much. Any question for the audience? The audience? Just a moment.
Hi. Like, I have a general question. Like, who will be, who has to take a more response? It's like if you look at the security systems, like it's telecommunication, like or like it's the government sectors who usually take the security as the primary concern. And it's like most of the way we are using right now the digital technologies through the cloud. So is it like if, for suppose, the people who are providing these kind of services, will they go for the post-quantum transition? Is it enough, or like
is it enough that the
is it enough for going towards the for suppose Cisco, like in there, if they can take care of like security systems, like is everyone has to like take the transition? Is it like if the people in the service sector, if they take care, it is okay? Like for suppose Apple, they announced their roadmap for transition. Like,
yeah, I understand. I would say the bigger companies, it's so the question is about is it enough that basically the government just take cares about the transition? No. It's I mean, it's if the government takes care, it's just we should do that. It doesn't mean it just happened like that. We have a huge public sector in Europe, and it's constrained in many ways, resource-wise. And I mean, if we talk about, for example, a municipality, is constrained competence-wise. It needs help. And with the transition, and it's both awareness, it's also the technical solutions and the process itself. So the way it's organized. And healthcare is also partly public and also private. It's a challenge, especially given the nature of the data they use, for example. So, and telecom, I would say it feels more safe because it's normally backed by big companies which know the about the problem, and we know how to solve it, and they work on that. Yeah.
How did they choose this Falcon and Lattice, like this kind of?
Yes, so this is, I would say, this work in progress, because you basically need to make tests and see the performance. And I would say for regular computer systems, it wouldn't probably be a problem. It will be a problem for smaller devices where you need to make compromises. And the work is, I guess, ongoing to create lighter versions of the algorithms which can be used for smaller devices.
There is one more question.
Thanks for a delightful presentation, Mikael. So in a hypothetical future scenario, say 20 years in the future, surely this will not just be like a European concern, but an international concern, right? Because there is a lot of data being circulated, which is, data sets with passwords, with personal identity information that has been RSA encrypted or encrypted with other methods that currently are not breakable, but could be breakable within 20 years' time. And in Europe, like, we have probably in 20 years' time, we will probably have control mechanisms that heavily guard what people can access our backends, right? The compute resources that are available to us. But it might not be so over the entire planet. Like there could be huge value in going through this whole, store now and decrypt later phase of like it could be an attack vector essentially. How is this question being driven not just on a European level, but also like in an international level between Europe and the rest of the world? How is the world like collaborating to understand how people are using quantum hardware to potentially like with harm's intent decrypt large troves of data? Is this known? Like, do you know anything about this? I'm just interested in how what the landscape looks like.
Now we actually so far we haven't gone. I mean, it has been focused on the Western countries and the Americas and also European countries in particular. Yes, and this is I would say it's a relatively new thing for many countries, and it's in particular in Sweden. So and basically I think this will be there. But it's a good question. Yes. I don't think it has been thought about.
Yeah, no, I realize you don't have the answer, but I was just wondering if you have any taps on how that is developing, like in general. Okay.
Yeah.
All right, well.
I'm also in the same area of research as Michael. I know there's also been reports from South Korea, at least, that in terms of like transition possibilities. I don't know anything about that. I just know that in Asia, there's also other entities that are trying to push some types of transitions, but he's right that it doesn't seem like there's much collaboration in these areas. And China is, of course, China, so who knows what their plans are. But it is a very interesting question as to what will happen in the next 10 to 20 years.
Thank you. Any other questions?
So for me, the cryptography, thank you for the nice talk, I enjoyed. For me, the cryptography, it's a deterministic kind of problem. So you need to, like with certainty, you need to encrypt and decrypt, right?
Yes.
But how this is compatible with the probabilistic nature of quantum computer and technology?
It's relevant in the sense that this is an application of a quantum computer. Maybe it's one of the, say, big driving factors driving the quantum computers, because it opens, I would say, a lot of possibilities. So it represents just the other side of the problem. So, and we say from the post-quantum resilience perspective, it's very important to, I would say, be and keep track on what happens within quantum computing. Because as I showed there, that there was a great uncertainty when a cryptographically relevant computer will come. So, and it might turn one way or another. Maybe we don't have that 20 years. Maybe we have just 10, or maybe we have 50. We don't know. That's why, I mean, often the people working with post-quantum resilience, they are present at these meetings trying to understand where it goes. So, and yeah. That's, yeah, and there is a relevant area called quantum key distribution, which is much closer to the quantum area.
Thanks.
I will read up a question from our online document, which reads as follows. Are the regulatory and ethical frameworks for quantum computing cryptography already in place through worldwide agreement, or just at preparatory stage? And how are these enforced in that case to ensure public and industrial security?
That was a question from the chat.
Yeah.
Because I don't see it somehow.
It's not from the Zoom chat, it's from our shared workshop document.
Oh, okay. Yes.
HackMD.
Can you repeat that one?
Yeah. So are the regulatory and ethical frameworks for quantum computing cryptography already in place?
Yeah.
Worldwide agreement or some such, or just at preparatory stage? Question one. Question two, how are these enforced to ensure that the public and to ensure public and industrial security?
Okay, I think there is a little bit of mix-up. It mentions quantum cryptography, which is closely related to quantum key distribution. So, and quantum cryptography is using basically the quantum effects to share information with the possibility to detect, I would say, an intruder. That's and the post-quantum, and there I'm not sure that there are actually. And here the post-quantum, has the same quantum word in the title, but it's an advancement of, I would say, mathematics in cryptography, which is called post-quantum cryptography. And there is I see this is just a defense mechanism. So basically in this case, unfortunately, the quantum computer is a threat, which it may cause problems, I would say, to all levels of the society, and this needs to be taken care of. So in this case.